Hello everyone, I'd like to thank you for being here today. I'd like to thank Professor Timar for his very good introduction. Heidi for giving me the chance to present my work and share the discussions with you today. And lastly, the DLR for funding this work. My name is Maxime Monette. I'm actually from Canada, but I'm working under the supervision from Professor Timar for about a year and a half now in Dresden. And I've been working on the Mach effect thruster, on Professor Woodward's drive, and on basically the design and if it actually works as designed. And I'm going to look at really the engineering details of it. And you'll see that me and Matthias are working collaboratively on this project, and we have a different approach to testing the Mach effect drive, and well, you'll experience it today. So I'm going to give a brief overview of the Woodward experiment, the whole setup. I'm really looking at the whole setup. I'm going to show you how we conducted an electromechanical analysis. I want to stress the importance of a good impedance spectrum of the Woodward thruster itself, but also the whole system. I'm going to show the differences between our system and Professor Woodward's. We're diving in Professor Woodward's theory. We assume that what he derived is what is causing the mass fluctuation. We want to replicate the thrust that he's been observing with the conditions that he has set himself up. And I'm going to look at all of these conditions and how they affect the experiment. We received a thruster from Professor Woodward himself. We tested that one at our facility. And we have also first experience of building our own thruster, so I'm going to walk through you through this process as well. I have also FEM modeling of the thruster and see how this will help understanding the Woodward thruster. And lastly, I'm going to introduce a few alternative experiments, as Professor mentioned previously, the magnetostrictive actuator, direct mass fluctuation measurement, and a few tests run in parallel with the Woodward thruster. So let me get going. So we've seen these thrust graphs in Professor Woodward's presentation. I'm really grateful that he did such a clear explanation and introduction of his topic. What we have in this diagram is an example of a difference between thrust measurement done forward and the thrust measurement done in the opposite direction. So we should see reverse in the thrust, and the difference should then give a net thrust. And what we see in this case is that we have, for about 200 or 150 volt amplitude in the thruster, we have about 0.8 micronewton. So this is what we want to replicate. This is what we want to see in our own experiment. We don't know, of course, what the power to thrust ratio is in this case, because Professor Woodward doesn't show the current measurement. So even if we know what the voltage is supposed to be on the thruster, we don't have an idea of what the power is, because there's no current. Anyway, so the Woodward thruster, you've seen it before. That's how it's explained. There's a tail mass, or the brass mass, which is kind of the heavy reaction mass at this end, connected to an aluminum bracket and separated with a rubber. And then you have the head mass, which is a lighter aluminum mass, which is supposed to be vibrating with a higher amplitude. And in between you have the piezoelectric actuator, which is basically a multi-layer stacked actuator that provides the vibration, so that provides the extension when a voltage is applied through the inverse piezoelectric effect. The important part is that Woodward uses a single sign to drive the piezoelectric drive, and then he relies on electrostriction to provide the acceleration to convert mass fluctuation to a thrust. And this is what I'm going to explain in more detail later. And he also has a step-up transformer to boost the voltage over the drive. Lastly, he also uses an accelerometer or a strain gauge in his stack to identify the mechanical resonance, although we've learned yesterday that he doesn't even use this mechanical resonance to drive the thruster. So he chooses a frequency which is outside of this mechanical resonance. So we'll see how much of this is consistent. So this is, I've tried to put his experiment, so some pieces might be missing, but the overall picture is that he has an audio amplifier. So there's a frequency generator which gives the a very low voltage signal to the Carvin audio amplifier, which then has limited frequency range. This Carvin amplifier we've seen at his lab, we went there last year, was limited to about 20 kilohertz, but of course it can be driven at 40 kilohertz with a small damping in the power. And the power that it delivers is load dependent. And the load will of course change with the impedance of the thruster, but not of the thruster only, but also the system composed of the transformer with the thruster together. That's mounted on the balance and inside a vacuum chamber. So question is, what is the power in? Because it does vary with the frequency you drive it at. And an element that we missed in our own setup was the step-up transformer, because we didn't see it mentioned in his papers. And I'm sorry that we might have lost the transformer. It could have been a problem in communication. Anyway, so we'll see anyway what the effect of a transformer should be on the experiment, and I'm gonna walk you guys through that. This is our experiment at TU Dresden. We do it a bit different. We perform the experiment overnight, 200 profiles of about 20 seconds, so that we can reduce the overall noise. We can average the thrust measurements over a whole night, and then reduce the noise as much as we can. And Matthias is going to talk to you about the experiment, the measurements itself. But anyway, we have an amplifier which is designed to be operating up till 200 kilohertz, and we have a power supply which can provide the voltage which was to be expected in the experiments from Woodward, about 200 amplitude. And we have the current supplied which can actually provide the power that the Woodward thruster needs at any frequency, so even at resonance, where the current would be higher.
Oh, quick question.
Yeah.
Do you record the voltage on each sweep?
Yeah, definitely.
So you know what the actuator is actually seeing?
Exactly, so I'm going to show that. So the characterization of the experiment starts with electromechanical analysis. Short detour with a small analogy with the harmonic oscillator. So let's assume that we have this multi-layer actuator which is fixed to a wall. We could compare this to a simple harmonic oscillator with damping and a spring constant, very basic analogy. And we can transfer this to the electrical representation of an RLC series circuit. And the only thing I want to point out with this is that, of course, as we expect, at the resonance frequency we have an increase in amplitude, but also we have a phase shift between the force and the displacement of that mass. And if we look at the impedance spectrum, which is equivalent in an electrical analogy, we have a dip in the impedance. So if there's a dip in the impedance, then there's a higher current for, let's say, a given voltage. And also we have, you can't see it really well because of the poor colors of this graph. There's actually a phase difference in the impedance. So the impedance, which should be minus 90 degrees for a simple capacitor, goes to 0. That's the phase between current and voltage. It goes to 0 at that resonance. So these systems are equivalent, and taking an impedance spectrum of the whole electromechanical system tells us a lot about the mechanics of the thruster. So this is what I want to stress here. Looking at the impedance tells us about the, yes?
What is 0 dB on your displacement?
0 dB, well, that would mean that it's almost not moving, but this is not a logarithmic, no, it is.
Vertical axis.
Yes, you're right.
Right there.
Yeah, that's a good question. I don't really care about the absolute value of the displacement. I just wanted to show the change at resonance, that it's amplified. Yeah, I didn't pay attention to that.
Maxime?
Yes?
Right when Dave asked you a question, you were saying that the impedance indicates the mechanics. Can you just say that again?
Yeah.
I think this is the main point, right?
Yes. Well, basically I show that if you compare the electrical circuit to the, if there's an equivalence of the electrical circuit to the mechanical system, which has been done this way, using standard conversion equation from amplitude to current and so on. I don't go to the detail of how I got to this. There is a phase shift in the impedance at resonance. There's a dip in impedance at resonance. And
in the real system or in your analog?
In this analog. And I'm going to show that in the real system the same happens, the same occurs. So this is just an introduction to stress the importance of impedance, of the analogy.
Although Maxime is right about the importance of the impedance spectroscopy, we have to remark that that model that is being shown there is completely invalid for anything that has to do for space propulsion or even for the experiments of Professor Woodward.
You're right.
Because, of course, you cannot clamp anything in space, and because the center of mass of that system is fixed. Where is the center of mass of that system? Is in the clamp, which is assumed to be so massive that it overwhelms everything else. So in that model, the center of mass is not moving, it's in the clamp itself.
So thank you, Jose, for pointing that out. It's good that people understand the difference.
I got another question.
Yeah.
Did you extend your frequency sweep beyond 100 kilohertz at any point?
No, because this one only has one resonance, and I'm not interested after that.
Well, I found that nonlinear effects always show up with odd order harmonics. So 105 would be the...
You'll see plenty of nonlinear effects in the Woodward once I get to the actual system. Well, that's the one. So it all starts with measuring the impedance of the thruster itself. So separated from anything, because the experiment should be designed using the thruster itself. So the thruster is designed without thinking maybe about what amplifier you're going to use, how are you going to mount it. And so the resonance should show up in the spectrum, the impedance spectrum of the thruster alone. So I went and used an impedance spectroscope, connected the thruster itself, and that's the kind of impedance spectrum that I get. So as I said before, when you have a dip in the impedance, that's where you have increased in the vibrational amplitude of the mass. So that's what we expect to be at this frequency, about 31 kilohertz. This is, by the way, the Woodward's thruster that we received at our institute. So that all made sense to us, that we have also a second resonance frequency, which is a result of the electrorestriction that's present in the material, so in the piezo stack. And we were pleased to see that that second peak where we have impedance dip, and so higher current, higher power, and increased amplitude was exactly at twice the first peak. So the frequency is exactly twice the first frequency. So we thought, okay, that's great, that's how Woodward designed it, and that's how it should work. That was our understanding of it. And in this impedance spectrum, you also see that the phase, so this is basically the impedance, the red, and in black you have the phase of the impedance, so the phase between current and voltage. And this will go towards zero, as I've shown in my previous diagram, when we have this resonance. And this is what we're seeing, but the reason why it's not exactly going to zero here, the first peak, the phase is not exactly going to zero, that's because the Q factor is not infinity, and there is damping, in other words. So you will not exactly reach 0 degrees impedance phase at resonance. So that's another thing is the anti-resonance. That would be a surge in the impedance. That would be very difficult to put any current in the thruster at that frequency. This is what this impedance spectrum shows. And when seeing Professor Woodward's graph yesterday, I was thinking that he may be driving his Woodward drive at an anti-resonance, because that would be where there would be an increase in the voltage. Because if there's if there's a constant power provided by the amplifier, but there's no current going in, then it's easy to spike the voltage, right? You know the famous voltage, current, resistance, or impedance relation, right?
Maxime,
Yes?
how long do you integrate for to get the power spectrum? Is it through the full cycle? Or?
Yeah, it's a standard procedure. I do as many points as I get, 500 points between 20 and 100 kilohertz, and that lasts about 1 minute.
There's the other diagram where you turn things on and you see the thrust. Is this over that whole cycle?
Oh no, that's different, because the diagram that I showed is a pulse that's performed by Woodward, so that's a fixed frequency. And what I'm doing here is I'm varying the frequency that I'm driving the piezo actuator at, to see how it responds, how the impedance is at a specific frequency.
It's a sweep.
It's a sweep. This is a sweep, and the thrust that I showed in my first slide is from Professor Woodward. It was an example of a pulse at a fixed frequency. Yeah.
My main takeaway so far is that driving a system at resonance optimizes power delivery. Is there something deeper I should be getting, or is that the main takeaway you're trying to convey?
That is, up to now, the main takeaway. You're right. So at resonance, the dip in the impedance, that's where you should get the maximal vibration. Thank you. All right, I'm moving on. So what if now I connect the amplifier, the oscilloscope, which I showed in the simple diagram previously, at the TU Dresden using Professor Woodward's thruster. I did the same kind of spectrum, but a different way. We drive it with our amplifier, we measure the voltage, and we measure the current over the thruster. So we use a Hall sensor to measure that current that's going in the thruster, exactly, and an oscilloscope measuring the voltage in parallel to the thruster. What happens is that we have small frequency shifts, but not a significant one at the frequencies we're interested in, so at 31 kilohertz. But we do have a lower Q factor, so a widening of that impedance peak. So we expect maybe a bit less of an amplitude at that frequency. This diagram, you have the voltage that we're actually applying to the thruster, which is 55 RMS, so about 80 volt amplitude. And we also have the current on the thruster. So this is actually the power that's going in the thruster. We can measure by just multiplying the voltage RMS to the current RMS. And of course the phase angle between both. But we'll see what we expect is that there's a surge in the current at the resonance frequencies, as I explained with my impedance diagram.
Quick question.
Yep.
On your impedance chart, what does loaded mean versus unloaded?
Okay, so loaded means that I'm testing the impedance of the thruster when it's connected, hooked up to all the electronics.
Okay.
Yeah, and also fixed on the balance in that case. So loaded means that it takes into account all the components that you're going to put connected to the thruster, and because it's an entire electromechanical system, they all have an influence on the dynamics of the thruster. Because, as I showed, the impedance spectrum is directly linked to the mechanical system, right? To the dynamics of the thruster. So that's what I'm looking at in this presentation. I also did vibration analysis using, yes?
If you just go back to that last.
Uh-huh.
The red line on the right hand chart.
That's the voltage over the thruster, which maintain constant.
Okay, and then the red line on the left.
That's the impedance of the unloaded. So that's the one that I showed in the previous slide. So if I test the thruster alone, if I test his impedance.
Those red and blue lines are purely impedance on the left.
Yeah.
Loaded and unloaded.
So this is unloaded, so the thruster alone.
Right. Thank you.
And this is connected to all the electronics. Yep. Of course, we don't have the same setup as Professor Woodward, so we're going to see what are these differences. All right, so I also did a vibration analysis because I wanted to see, well, do we actually also have that mechanical resonance at the electrical resonance which we measured and which we would expect to be consistent. And that's what I see from this diagram. So that the mechanical resonance shown by the maximal amplitude of the aluminum mass corresponds exactly to the impedance dip. So at both of these resonance frequencies, these two, I have also an increased amplitude in the movement of the aluminum mass. So I should have explained how I did the experiment, but it's pretty straightforward. I have fixed the Woodward Thruster this way to a fixed bracket, to optical table, and then have pointed the laser of the attocube directly on the aluminum mass as close to the center as I could, and then seen the waveform, and then did a Fourier analysis to obtain the maximal amplitude of the displacement. So that's the secret behind this diagram. Yes?
So this is the thruster as received. You didn't go and retorque or anything like that, or experiment with torque values on the bolts if it changes the stiffness of the structure?
Yes, exactly. So in this picture, it's not it's the thruster that we built ourselves. The difference between our thruster and Professor Woodward's is that he has a thermistor at the end of his aluminum cap to measure the temperature at that specific point, and so that means we cannot put the laser at this place, and there was very few room to put our laser, but we maintain everything as received with Professor Woodward, and we found a spot where we could polish the aluminum and get enough reflection for our laser, but it's not exactly at the center, so there could be a bit of a discrepancy there.
What is the frequency response to the attocube detector?
It's 2 megahertz. Something.
The bandwidth is 10. It's 10 megahertz.
10 megahertz.
So yeah, you can see it pretty well.
Yes.
Where you say that the displacement, maximum displacement, it means the maximum displacement of vibration, not the displacement of the thrust. Is that correct?
Right. It's just the aluminum mass. So I'm looking at the aluminum mass and not at the other side. The other side could be moving too, right?
In other words, when the experiment for the thrust is set up, you have supposedly a movement of the torsional pendulum.
Yeah. This is not how it's set up on the thruster,
right.
On the balance.
This displacement is the displacement due to vibration itself. Nothing to do, it's nothing to do. It's a different thing from the actual.
I'm going to get to that, so be patient, but yes.
This experiment, he registered a 13 nanometer displacement. That's in this paper.
Okay.
He did this experiment as well.
So, but his laser interferometer has not such a high frequency, so it's very hard to detect frequencies of 30 kilohertz with.
Did you guys look at the bracket?
We didn't look at the aluminum bracket itself, right? Yeah. No, that's something that has to come up to distinguish how the rubber actually damps the vibration of the brass. This experiment still has to be done. Yes.
So actually, from what you're pointing out there, it looks quite advantageous because you're showing that the peak currents correspond to maximum displacement, and if what you're seeking is to have the maximum displacement of vibration.
Yeah.
If that is the case, then at the resonance, the strain gauge is not a pure accelerometer, because we know that to be a pure accelerometer, the strain gauge has to be much below the resonance. And therefore, if this is a better measure of what you're looking for, then you get away from having the strain gauge in the stack itself.
Yep. Thank you. That's one of the main points. We don't need to use the accelerometer signal. That's just a superfluous signal that we can ignore by doing this experiment.
Which is not a perfect accelerometer anyway. Because
yeah, but you could argue that you don't need the exact value of the strain gauge.
right.
You just need to see the resonance, right?
I agree.
Yes.
Did you measure other locations on the aluminum disc to see if there was flexing of the aluminum disc?
That would require me to do many points on this. It would take a lot of time, but I am doing a FEM analysis, which then would give me the, if it's perfect and corresponds to these measurements, it would allow me to know the exact displacement of each of the parts, and that's also very interesting. So that's also what I'm doing.
I hate simulation. Only as good as the information you feed it.
Yep, it's very difficult.
Something like this, like a really high resolution up close LiDAR that can scan the entire surface of the cap.
Yeah, in Dresden we probably have the facilities that do that. It's maybe a contact away.
Very expensive.
But it's very expensive, exactly. So, but it's probably a contact away. Maybe I could.
Yeah. That resolution of frequency.
Mike?
I was just going to ask if you could comment on the higher displacement at 30 than 60 kilohertz, because I thought in your previous plot you had much higher power deposit at 60 than 30.
Yep. Well, the way I see it is that it's the second harmonic, and that usually the second harmonic show a lower amplitude of vibration, just because it's a second mode, and then that the overall displacement is then not as big as the first mode, which is
higher damping for higher modes usually.
yeah. This is the way Professor Woodward does his experiment, and we have seen this thrust kind of sweep yesterday, where he does a frequency sweep. This is the voltage of the frequency generator, so we don't really know what the frequency is unless we know what the center frequency is. But anyway, we see how the voltage is changing. So it's not exactly how we're doing it, where we actually maintain the voltage, because that's we think that the voltage tells a lot about the thrust. So we can expect a thrust at a specific voltage. But here the voltage changes with the frequency because of the impedance of the thruster, right? And we see that, well, this is the strain gauge, and it also shows the mechanical resonance. And yeah, yesterday I've already talked about this. We've seen that Woodward picks not the mechanical resonance, but another electrical resonance. So when we actually look at how the voltage is recorded, we can see that it doesn't assume a perfect sine at resonance. So which resonance it is, we don't know in this picture, but this leads us to think what exactly is the voltage going in, the power going in, and therefore we would like also to see impedance spectrum or power spectrum of the loaded system of Professor Woodward's experiment. Then we come to the point of the transformer. So Professor Woodward uses a step-up transformer, we didn't. And that could be the explanation as to why we didn't see any thrust. What does the transformer do? It should not bring any phase difference in the between the voltage and the current. It actually just boosts the voltage and divides the current. So if we want to have 200 volts over the thruster and we use a transformer, then that means we would only require a higher current at the source. That's basically the principle of using a transformer. But if we already have the voltage capacity in our amplifier, so the amplifier is able to provide 200 volts at the frequency we're driving thruster at, then we don't need a transformer, because yeah, that would bring extra effects to the thruster, to the electromechanical system, because actually a transformer is not ideal. It has internal resistance. It can be magnetically saturated depending on the core that you use it, and so it all has these real effects that could change the spectrum of the thruster. So is this working as designed, or is Professor Woodward just picking a transformer and then finding a lucky resonance? I'm not sure about this. So I'm here at this conference to know what what this transformer is supposed to do.
Well, the transformer is an impedance matching device.
I'm sorry, I didn't understand with the coughing.
The transformer, generally speaking, is an impedance matching device.
Okay.
So that's a function of the transformer.
What type of voltages are you talking about?
200 volt amplitude.
So you guys have that naturally anyway, compared to 120 over here.
No, he also used about 200 volt amplitude. Yeah. But about the impedance matching, it changes. It could change the impedance of the thruster. And the thing is that Professor Woodward's amplifier delivers power based on the impedance of the thruster. So that's the problem that we have. We don't know what power gets delivered to the thruster because there's no current measurement. But if the theory is about displacing the electrical resonance of the whole system and then introducing some phase between the mass fluctuation and the acceleration, then that could be something that needs further investigation. And I'm gonna talk about the relationship between the phase between mass fluctuation and acceleration. So let's see what I have there.
One other thing about this.
Yes.
Every transformer has leakage inductance based entirely on the geometry of the windings. So that will create a series-tuned circuit with the capacitance of the actuator, which will greatly affect the response at a frequency to which it's sensitive.
Well, we did the experiment with a flyback transformer here. 6 to 1.
Very high leakage inductance.
Very high leakage inductance.
Yes,
okay.
huge.
We have a 6 to 1 turn ratio, and although we saw that the voltage this time is not maintained, there was a collapse of the voltage at the resonance because our amplifier was not made to supply the current in the primary circuit of the transformer. And so we also have a spectrum current spectrum which doesn't make sense. So, but when I plot the impedance by just dividing the voltage by the current, I get the same impedance of when I run without the transformer in my system. So, as expected, with any transformer, okay, it could be because we're not picking the right transformer, we don't see any change in the impedance. So, any phase in the resonance, or from the first resonance to the second resonance, there's no relative change between those. Okay, last point is about the electrorestriction, because I want to make sure that we're all on the same page here. I really like this explanation from one of God in piezoelectric material from Penn State University, Kenji Uchino, and he explains piezoelectric and electrorestriction the following way. You have on the right a centrosymmetric material like table salt and ACL, and on the left non-centrosymmetric material like a piezo material. Of course, it doesn't represent the 3D effects, but it's a good 1D analogy. You have in the centrosymmetric material the same spring constant between the ions in the lattice structure. And in the non-centrosymmetric, you have both soft and hard springs between the ions in the lattice structure. And so when you apply a field to a centrosymmetric material like NaCl, then you would expect the negative ions to be pulled and the positive ions to be pushed away by the same kind of displacement, so you wouldn't observe an overall deformation in the lattice parameter, so the distance between two consecutive positive ions. But in a non-centrosymmetric, where you have different spring constants between the ions in the lattice structure, you would get total deformation, because you would the ions would be displacing themselves relative to each other by different amounts due to the differing spring constant. So this is how piezoelectric deformation could be explained in a 1D representation. And what's special about electrorestriction, or how it arises, is that the spring between the ions, which is basically just the electrostatic Coulomb force and the quantum mechanical repulsion force competing for each other, this is not a linear spring. It's actually, it has a nonlinear spring constant, so it's harder to contract than to expand. And this gives rise to electrostriction, to a total deformation, which is available in all materials and is amplified in some materials like the magic cube, which Woodward tested, relaxer ferroelectric material. It is in all materials, but it is a much lower amplitude of displacement than the piezo effect that we see in PZT4, hard piezoelectric material. Because this electrostrictive constant, which is given in the literature, could be 8 orders of magnitude smaller than the piezoelectric constant, the piezoelectric coupling constant, which gives the displacement in relation with the voltage that is applied. So I have a question about electrostriction, and I haven't found the answer yet. Does electrostriction get amplified at resonance? I'm assuming that because it acts like a spring, it does also get this resonance, so the electrostriction is also amplified. And that's why I think Woodward is designing his experiment on, that he uses the resonance of electrostriction to get a higher amplitude at that second frequency to create the thrust. But let's see how we can go about thinking about how this mass fluctuation can be generated. This is a free body diagram of the thruster, and I know it's not the right connection to the balance and so on, but I'm focusing on actually the thruster this time. So you have a brass mass, aluminum mass, piezo stack in between, and these are compressed by steel bolts. If I look at the equation of motion, I cancel the force of compression, because this is basically cancelled by the compression of the actuator pushing on the aluminum cap and the bolts pulling on the aluminum cap, so this gets cancelled out. And the other components of the force that I have are then the elastic force, the potential spring force of everything that's connected to the screws, the brass, the aluminum, and the spring force of the actuator itself. I also have a hysteresis force, which is basically a damping force, which arises in piezoelectric material due to the internal friction that's in the piezo material itself. So you have rotation of the domains, and then also then viscous friction inside. So all of these forces also give rise to energy components, and if we look at Woodward's equation, which indicates a mass fluctuation due to the change in energy, internal energy density of the Woodward thruster, my question is which part of these energy components gives rise to that mass fluctuation? Increase the change in energy due to the maybe the acceleration, so the kinetic energy. So if we have a larger acceleration, then we could have a larger change in the energy density of the thruster. It can't be the energy loss because it's a small component. And also what's happening here is that you apply a voltage, and so there is a force due to the inverse piezoelectric effect which pushes the aluminum mass. But this energy, this mechanical energy which is produced by the actuator, is not directly the power that you put in, because there's also electrical energy which is stored in the actuator itself, in the condensator, in the capacitor. So which part of this energy creates a mass fluctuation? What if you have a transformer? You also change the energy in the transformer. Do you have a mass fluctuation in the transformer too? Anyway, regardless of where the mass fluctuation comes from, we would expect it to oscillate with the same frequency as the signal that we've put in. It's actually twice the frequency of the signal that we put in, due to how, well, I can write it on the board if I have a few moments. Because Because the mass fluctuation is basically proportional to the second derivative of the energy density, or proportional to the first derivative of the power or mechanical power, depending on the energy portion that you vary. The power we know to be force times velocity, and this force could be, for example, the elastic force of the spring or of the actuator itself, and this would only be the first derivative of the amplitude. So we'd have this is caused by the frequency signal that you're putting in, so it also oscillates at the same frequency as the voltage signal you drive the piezo at. And the velocity is just the first derivative of that amplitude. So you would get this squared component of that sine that you're driving the piezo at, and therefore you have that 2 omega in the mass fluctuation because of those dynamics. So the mass fluctuation has actually that 2 omega component. And to produce a thrust, you have to multiply it with the acceleration. So according to Newton's second law, that's how there could be a thrust if you have a mass that's fluctuating. Then you're pushing and pulling. You need that acceleration to actually make some thrust out of the mass fluctuation. Yeah.
What is the origin of that acceleration you have there that is A sine omega t? What is it?
Very good question. So point is, there's a mass fluctuation, there's an acceleration that you need to transfer it into thrust, and if it's to be a steady thrust, a unidirectional thrust, you need to integrate it over the cycle.
But is the acceleration of the center of mass, is acceleration of what?
I think I'm not even considering as to where the center of mass is. I'm just thinking basically if you have a static point and you're pushing on a mass that's fluctuating, you would need to have an acceleration which is in phase with that mass fluctuation to create a thrust. So I'm not looking at that yet, Jose. It's not my point. So
looking at a system where you're trying to match the mechanical and the electrical system. What is the damping factor do you have for the mechanical system and the damping factor for the electric system?
That would change, of course, the thrust that you're expecting. The damping would change the phase between the mass fluctuation and the acceleration.
How much of a variation are we talking about?
I'm going to show it.
All right.
I'm going to show it. So if you do consider a thrust which is made from a mass fluctuation, wherever it comes from, you need an acceleration, and you would need this acceleration to be exactly at the same frequency as the mass fluctuation, which is shown in this graph. Because so this graph shows basically the integration of a thrust over 1,000 cycles if it's composed of a mass that's fluctuating and multiplied by acceleration, which is also a sine. So if it's not exactly at the same frequency, then over just a few cycles, you would get zero thrust. So they need to be exactly at the same frequency. So you need to push and pull exactly at the same frequency as the mass fluctuation. And if there's a phase between the acceleration and the mass fluctuation, then we expect actually just a factor of a half if you're off by 60 degrees. You would have a thrust which is changing direction if your phase is between minus 80 and 60 degrees, but you should still see the thrust if the effect of the phase relationship between the first and the second signal is just a factor of a half by 60 degrees, right?
I object to that being called a thrust, because it's not a thrust. Because again, a thrust is something that acts on the center of mass, and you cannot push the center of mass in something in space by putting any, you cannot push it. Where is the push coming from?
That's a good point. Actually, how exactly the center of mass is moving is explored by Jamie, and I think he did a good job on this. and also by Keith Wenzer, right, in his paper.
Yeah, to me, any one-dimensional model doesn't make sense. The minimum model of complexity has to be, in order to explain this, it has to be, I think, at least a quadruple. It has to be at least, it cannot be a one-dimensional model.
Point taken. But if I can actually see a thrust just by being in a fixed position, because that's where it could be possible on the thrust balance. Let's say my beam is not moving at all. Let's say the beam of the balance is not moving at all, and I'm just pushing and pulling a fluctuating mass. Can I see a thrust based on the of the pivot on the balance?
Okay, but you're pushing it. Therefore, you're doing the thrust. Whatever is pushing it, not what being pushed.
Well, the point I'm trying to make here is that if you do have a mass that's fluctuating, and that you can accelerate it based on the center of reference that you pick for this thruster, when do you actually get a thrust? And that's only when the mass fluctuation and the acceleration have the same frequency. And if there's a phase between the two signals, there will be a minimal effect. It could change the direction of the thrust. But this is an interesting discussion, and we also have to look at this. But I'm showing here an example scenario of how this mass fluctuation can be generated, and that second signal, the acceleration, how it is also generated. As said before, Professor Woodward uses electrostriction to provide that acceleration component to convert the mass fluctuation to a thrust. So what actually happens here is that I assume that you drive at the minimum impedance so that you have an increased amplitude of vibration. And then you would have to have the electrostrictive signal, which is exactly which is depending on the squared of the voltage of the electric field. And so it would occur at exactly twice the first frequency that you're activating the piezoelectric actuator at, right? So on the impedance spectrum, you're actually here with the acceleration signal, and here with the mass fluctuation signal. So you have a phase between the first signal and the second signal. And this you cannot control because the electrostriction happens at exactly twice the frequency of your first signal. So you cannot control the phase relationship between the second signal and the first signal. And this changes with the impedance spectrum. As I've shown before, it changes on the loaded system that you have. So it varies with the amplifier that you have, varies with the mounting that you have for the Woodward thruster. So it's very difficult to control. And second of all, with the second signal, the acceleration being due to electrostriction, the second signal is very minimal because it depends on electrostriction, which I've shown before has a very small coupling constant, about 8 orders of magnitude lower than the piezoelectric coupling constant.
Okay, this is another thing on terminology. The electrostriction the excitation frequency has to be at the subharmonic of the natural frequency, not as a superharmonic. That means, for example, if you're looking at the 2 omega t, then the excitation frequency has to be at half the natural frequency. Are we in agreement or not?
No, I'm not in agreement.
Okay, well.
Not if you DC bias it. So
yes, it does.
Then the frequencies would be
no,
the same.
This has to do with any nonlinear vibration. We put mx dot double dot plus kx, or you can put the damping term, right, equal to some forcing function. And you have on, well, if you want, I can write it down.
Yeah, could you write that?
So let's start with mx double dot plus kx equals 0 in the free system, right? You have x equal a cosine omega t Therefore, x double dot is equal to minus a omega square a cosine omega t. Replace this here, then you get minus omega square a cosine omega t plus, sorry, here, plus m plus k a cosine omega t equal to 0. This cancel out, and therefore you get that omega square is equal to the square root of k over m, the natural frequency. Now, if we put here a forcing function. In order to excite this, you have to do this as cosine omega excitation frequency time. In order for this to be resonant, then you need to have omega excitation equal to the natural frequency. Right?
Yeah.
Okay? Now, let's do the electrostriction. There you have mx double dot plus k x equal a.
Can we do this after?
Because I actually have just 2 seconds. Cosine 2 omega t. Right? So you have now you're going to have the omega excitation got to be 2 omega excitation. This is the excitation got to be equal to the natural frequency. Therefore, omega excitation has to be the natural frequency divided by 2. This is the theory of nonlinear vibrations. You have a nonlinear spring here. This could be a cubic that's called the Duffing equation.
Okay.
Then you get the third harmonic. Then if you have the Matthias equations and so on. So the main excitation has to be at the subharmonic.
To have the resonance of the electrostriction.
Yes. Yes. So the excitation of the electrostriction has to be at that.
Really wasn't move on.
Yeah. All right.
Why is it that you don't like this to be clarified?
It is reprehensible and offensive to my intellect.
But what is the sense?
You're hiding to second my opinion.
What is the sense of being talking about electrostriction if you are very confused about it?
I'm only joking. Your point is well taken, but we must move on.
But it is no point in moving
Now the
on
mic is back.
in a workshop. If we don't have a common language here, if people think that this is a confusion.
It's a good point, but what you're pointing out is the natural frequency due to the electrostriction in the system, right? But the electrostriction, the amplitude due to electrostriction depends on the squared of the electric field. So if you have a voltage signal which is applied with a frequency omega, then you will have an amplitude response which is squared to that voltage, and so it would respond to that voltage signal at twice the frequency, right? Simple math.
You know what, just let him come to me for a while. I know, but you talk about it.
So if the second signal is not electrostriction, so if we have a mixed signal this time, with the second signal being also a piezoelectric signal, then we can increase this acceleration component to increase the overall thrust. So the integration of the thrust with mass fluctuation times the acceleration should be also orders of magnitude higher, because this inverse piezoelectric effect should be higher than the electrostriction. Furthermore, you can also change the phase by applying an additional phase to the second signal. So you can actually make it so that the second signal also have the phase that you're expecting for getting a higher thrust. But as I've shown with my previous graph, the effect of the phase relationship is minimal. These are graphs that show that an increase in temperature and lasting material damage also change the spectrum of the thrusters. But because we're short on time, I'm going to show this one first. This is an impedance spectrum of our thruster, and I'm going to show how different it is from Professor Woodward. But basically, what we have to take away from this, if we do a frequency spectrum of the thruster at 10 volts versus a frequency spectrum of the thruster at 180 volts, and then we have a dramatic change in the impedance spectrum. So much lower Q. And a shift in the frequency, a shift in the resonance frequencies, and also between a relative shift between the individual frequencies. So if you're designing a Woodward thruster based on its impedance spectrum, which is unloaded, and you have the nice peaks, with the second peak being at twice the frequency of the first one, then you'll see that all this goes to the trash when you write it actually at 180 volts with the current that can be supplied at that impedance, at that frequency. This would also really change the thrust. So how is our thruster different from Professor Woodward? Because if I compare, do I compare the, no. We also had different peaks in our impedance spectrum, so let's see how it differs from Professor Woodward's. What we did is to apply silver epoxy to increase the conduction between the individual piezo discs. And we actually welded or soldered the copper electrodes together before assembling the stack, because we solder these copper electrodes at around 350 degrees, and the Curie temperature of the piezoelectric material is around 320, so we don't want to go above that to cancel the piezoelectric effect in the material. And this is the reason why we did it this way. The problem with this is that it was difficult to align the disc because of how the cables were pulling on the electrodes, and even a tiny fault in the electrode could then disbalance the whole stack.
You could use Litz wire.
Litz?
Litz wire.
Litz wire.
It's very flexible because it's very, very fine wires, used multiply.
What was the resistivity?
But can it go in the vacuum?
Absolutely.
Okay.
Absolutely.
Yes?
What was the resistivity of the silver epoxy? Because I know it's typically a lot less than regular copper.
A lot less than regular copper. Did we measure the? No, we didn't measure the resistivity.
It's on the data sheet. It's good. It's good. It's not as good as solid.
But in any way, it would be better than the epoxy that is traditionally used between the discs. We aligned the stack under slight compression, and then dried the stack at 65 degrees to make sure that the epoxy sets. And yeah, so we run into some problems due to pulling of the mechanical cables, and so we had to use less bolts than what Professor Woodward is using, decreasing the stiffness. But also we don't have the American bolts, so we have a slightly different diameter in our bolts, so that our discrepancies between ours and Woodward's changes also the resonance of the thruster. We applied the torque of between 2,500 psi, so 15 megapascal around. And we applied thermally conductive epoxy on the stack to damp other vibrations and make sure that it was protected from humidity. And that had the actual effect of damping some other.
So sorry, did you cure this at 60? Was the epoxy
65.
65C? Or
Yeah.
was it right? It was cured.
Yeah. And so it damped a bit of the vibration. So this is, the red one is without coating, and the blue one is with coating. And this is done at a very low voltage, this impedance spectrum. And it shows how extra vibrations which are not desired are damped out. So it did the job. And this is the comparison between our thruster and Professor Woodward's thruster. Now my next question is, if we would conduct an impedance spectrum or a frequency sweep of his thrusters, would we get this large of a variation between his thrusters, or do the peaks always stay at the same place? Is it, is there a lot of uncertainty between the productions?
We discovered that there was a slight problem with the curing of the epoxy that we were using.
Okay.
Apparently, Jim was using an older standard, and we have now bought an oven as well, since our oven we were using, I hate to admit it, but it's like a 30-year-old toaster oven, which has very bad tuning, you might say. It only has like the first knob.
Okay.
That's like 250C, which wasn't very helpful. But we did have a thermistor inside the oven, but still we're getting a new one. And we are going to also try different temperatures for the curing, and then decide different procedure for the curing.
Okay.
So we did find that if I change the timing of the curing, I could slightly shift the spectrum a little bit.
Okay.
Not very much so, but just a little bit.
And it.
I'm thinking that we can just try this with sort of virgin stacks that have never been cured before. So I tried it on one that had already been cured.
Okay.
I managed to change it a bit by curing it at the same temperature, but 4 hours. And it did change it slightly. I was actually going to show you that in a little 10-minute talk.
Okay. Thank you.
Why do you change the temperature and the time? Isn't it specified in the data sheet of the epoxy? How
Yes, it is.
long?
Unfortunately, he's using the same epoxy for like 30 years, and the timing has changed all that time. So, not the same epoxy, but you know, he was taught by someone who was an expert to do it a certain way.
Which one of these is yours?
Yeah. The blue one is ours, and the red one is Professor Woodward's. So this peak actually is what I expect from FEM, from modeling. And there's a second peak right next to the first resonance, which I don't know where it comes from. But so basically the unloaded impedance spectrum would be a very good way to characterize your mechanical systems and make sure that it's built the right way, or built as designed. And I would be interested to see what difference the dome configuration, or the way you clamp it with the brass mass, Jose, would have on the impedance spectrum. Because
the issue with the curing is this. The state of cure of the epoxy is characterized, it's a thermoset, so it's characterized by a transition called the glass transition temperature. Okay? This system is capable of having a glass transition temperature of about 100 degrees C, and it has been known and specified that a preferred cure cycle for a specimen that is free is 100 degrees C. Now, that is for an epoxy that is completely free. Now, when you are bonding epoxy to metal, then you know that as it comes down from the glass transition temperature to room temperature, you have residual stresses because it shrinks. The epoxy wants to shrink, the metal doesn't. That puts tensile residual stresses which will crack the epoxy.
Yep.
Therefore, the optimal cure temperature for such a system is unknown. It is not something that can be obtained from a material specification. It has to be found out by a trade-off between residual stresses and the optimal cure for the epoxy without taking into account the bond. That is the issue.
Very good point.
And there's something that was not properly done.
And it's something that will vary a lot with because we used a different epoxy.
Exactly.
Okay, good. So that could be an explanation for these other peaks. All right. So I've also dipped into FEM because I think it's a good visual representation of how the thruster should move. Unfortunately, it's not on the balance, and I want to do exactly what Jamie did. I think it's fantastic. To model the whole balance and the flexural bearing, I think that should be the objective of a good simulation. But my objective with my simulation was to know exactly how the individual parts in the thruster are moving. And if I can get all of those, then I can get a better estimation of the energy components which are fluctuating in the thruster, and then get a better approximation of the mass fluctuation predicted by Woodward's theory and the thrust that can be predicted. So yeah, that's the system I go through when doing my modeling. Of course, I have to take a simpler model so that I don't have problems with contact interface and other details like the head of the screws and so on. And I have to implement also all the piezoelectric properties according to the ANSYS format that requires a lot of juggling around. But I got all those information from eFunda. This is a site, very good site that gives the piezoelectric constant in 3D and the electric permittivity. So with a constant strain, so I have to convert it. eFunda.com.
Will your modeling show the reflections between dissimilar materials as the acoustic wave moves through the material?
No, it would just show the deformation, how the elements move in the structure.
I don't think that's ever been addressed.
That's basically how what the result of the simulation looks like. So I have, of course, an amplified movement. So it does not actually move like this in real life, but it's to show exactly how it does.
I have looked at that, and they are higher frequencies. So why would that be relevant to something that is operating at 35 to 40 kilohertz?
Reflections?
Yes.
You have standing waves.
Extremely small amplitudes.
If you have a quarter wave difference between reflecting surfaces, you have an infinite impedance.
Of something that has extremely small amplitude by orders of magnitude.
Doesn't matter.
So my first simulation
We know it's non-linear.
gives me the amplitude at the first resonance and at the second resonance, which is not exactly twice the first resonance. So I was going about thinking, why would that be the case? Even though that also seems to be a longitudinal mode, a second longitudinal mode. So I had to implement damping in the piezoelectric material. And the one that was suggested by the literature for hysteretic damping is the beta, so stiffness proportional damping. And this varies with frequency. So the loss in the material will vary with the frequency you're driving the piezoelectric material at. So this had to be implemented for a frequency-specific simulation. So this gives me a pretty good order of approximation when I compare the amplitude of vibration as tested on the optical table with the laser and with my FEM simulation. So 50% accuracy, I would say. But of course it can be improved. But the most concerning is that the second peak is missing. And this could be because there's no electrorestrictive properties that's ever been implemented in FEA. So this would have to be done, or there could be a trick using a secondary piezoelectric effect with a smaller order of piezoelectric constants.
My model shows that this is due to the fact that your Raleigh damping is damping higher frequencies received, and that is a reason for this.
But actually, I do change the damping. I actually superpose two simulations. So I do one simulation with hysteretic damping with this value for the beta at the first frequency of resonance, and the second simulation for higher frequencies I would do with a damping with the second resonance frequency.
Yeah, are you able to have that second damping value change at will? And if so,
yeah.
Can you, if you decrease the damping, then the second mode is going to get higher and higher?
Yeah, I mean, yeah, that's what I do, because actually I implement the experimental Q factor to determine the damping constant, and then I take the Q factor at the second resonance frequency to get me a second damping coefficient.
What I'm saying is, in your model, increase the second Q value to a high value enough in order to have a response similar to the blue.
Okay, we'll see what that does. All right. Yes.
eFunda you mentioned didn't have any electrorestrictive constants, I assume.
It did not have the electrorestrictive. Yeah. It's. I mean, it's not something that's being researched. Even there's no experiment showing also the resonance of electrorestrictive.
Because it's extremely small amplitude.
Yeah. So, well, that's something that we're working on. See if we can detect electrorestriction.
But let me, sorry to add this, but we have, from the experimental point of view, we know that it is distorted wavefront, but has there been an analysis experimentally to show that is due to electrorestriction? Because it could be due to something else, right?
You have a distorted waveform, but that could be because of the amplifiers at its limit.
Exactly, that's what I'm saying.
Yeah.
So even the issue of whether electrorestriction is involved, you have to have an open mind.
Definitely. Yeah. This will be addressed when we do another experiment, which I have, that's coming up. I'm almost done. So this was looking at the difference between having a rubber, because that was with our own thruster, we can change things around. So we tested the vibration with a rubber and without a rubber. And I still have to do the experiment that Jamie mentioned to look at the bracket to make sure that the rubber decouples the motion of the brass to the bracket. But having a rubber or not changes, well, it doesn't change actually the amplitude that much. It seems to shift. So the red one, sorry. The graph on the left is the aluminum displacement. So I'm looking at the aluminum mass with my laser, so seeing how it's moving. And the graph on the right is the displacement of the brass. So I'm on the other side with my laser and then looking at how the brass is moving. So in between, so in the bracket, looking at the brass, not at the bracket. And the blue curve is with rubber, the red one is without rubber. So on both graphs that's the same. And we'll see that there's a shift in that frequency. The two peaks are still there, but the second peak seems to be amplified when I have rubber. And it's the same order of magnitude for the amplitude, it's the same amplitude. And in the case of the brass, it also moves quite significantly. I mean, it's the same scale for the aluminum and the brass. So the brass also moves in that other direction as predicted. And the addition of the rubber doesn't really damp the brass itself. So the brass still moves. And yeah, tests with the decoupling with the bracket are still coming up.
Quick question.
Yep.
Have you tried putting rubber under the mounting bolts to the mounting bracket so there is true isolation of the brass? Because right now, as I understand it, the head of the bolt is against the bracket,
Yeah.
which still provides a very tight...
But that will be always the case because the bolts are screwed in the brass mass.
Right, right.
There will always be a mechanical connection.
But
So
if you put rubber there, that'll help decouple that.
you would have,
He's suggesting a washer under the head of the bolt going through the brass mass. That's what he's suggesting.
okay. So you would not actually have a mechanical connection between the bracket and the screw.
But only with rubber isolation between the mount on both sides of the unit.
Okay.
No, but hold it here. This is a very important experiment that goes against what people were saying about the rubber. And this is an experiment, right?
Yep.
And it agrees with what I expected from the rubber, which is different from what people have been saying. The blue curve is with the rubber, correct?
Yeah.
Now, people were saying that the rubber has a modulus of elasticity which is many orders of magnitude less than metal. So, according to what people were saying, that the rubber was decoupling and so on, when you have the rubber, you should have a lower frequency. But look at what the experiments are showing. When you have the rubber, you have a higher frequency. Right?
Resonance, yeah.
You have a higher resonant frequency. Resonant frequency goes like the square root of the stiffness divided by the mass. Therefore, the train of thought of people that say, here, the rubber is doing this, is wrong. This is shown here in the experiment.
But
Number two,
you're having much smaller metal in the bolts.
let me tell you why. Now, but the people that were saying this model, they are wrong. This is what the experiment shows. Number two, people are saying that the rubber is also providing damping. What does your experiment show?
Well, I would have to look at the bracket movement.
Okay.
And I didn't. I have to do that.
So far, what does it indicate?
Well, this indicates that the brass movement is not damped.
Right. So again, these expectations are shown to be wrong. So what is it that the rubber is doing, and this is done in aerospace and so on, it is just addressing the contact problem. It is not, as people are naively thinking,
not that simple.
without doing, no, you can do a simple analysis because the spring stiffness go like 1/k, and you can do this in the back of the envelope to show what the rubber is actually doing.
So it smooths out actually the amplitude of the brass mass because it solves that problems with the connection to the bracket, right? This is actually what I've also observed, and it's not in this presentation, but that if I look at the displacement of the brass mass, it's actually distorted when there's no rubber. And when there's a rubber, it's a smooth sign.
Exactly what I expect.
Okay.
That's why in aerospace, if you're going to put anything together and you have to go through thousands of cycles, by cycle fatigue, you're never going to connect to something solid. You have to address the contact problem.
Okay.
Could you consider suspending the thruster so that there's no mounting bracket, and look what the displacements are on both the aluminum and the brass?
On a frictionless track. On a frictionless track on a supercooled superconductor. A pendulum. Okay. Well, I mean, there would be electrical connections to the thruster, so that would also bring some uncertainty. So, but think about a way to do that. I'm interested in that as well. If I change now the pre-stress on the bolts, what sort of effect do I get? I don't have any. There's no change in the impedance spectrum or the resonance frequencies in the thruster.
At what?
At between. This is at. This should be around 20 volts. Okay, but anyway, the voltage is maintained constant for all those experiments, so it's consistent, right? I'm not looking at the effective voltage here. I'm looking at the effect of the pre-stress provided by the bolts. So between, okay, this is SI units. I'm not sure if you guys, between 15 megapascal and 25 megapascal. That's between 2,000 and 3,000 psi. There's no difference, no noticeable difference. But if I drop below 2,000 psi, then I change the Q factor, the resonance frequency, the anti-resonance. So this is not desirable. So there's a threshold of compression that is required to increase this Q factor, the amplitude that's to be expected.
How many MPa?
Between 15 and 25 MPa is good. And from the literature, we don't want to go above 30 MPa, so we didn't do it not to affect the material properties.
And you don't want to be below 15?
You don't want to be below 15. All right.
How much is that in PSI?
Yeah, 2,000 PSI, I would say. But double check to be sure. Experiment number 2, magnetostrictor. This is actually an ultrasonic transducer that uses magnetostriction. If you guys are not familiar with what magnetostriction is, it's basically what produces the hum in transformers. So that humming sound is due to the expansion of the ferrite core, which is in the solenoid in the transformer. So that is a mechanical vibration. So that produces the sound, the noticeable sound. And so the way it happens is that you apply magnetic field, and then the magnetic domains in ferromagnetic material will then rotate to then extend the overall lattice structure. And this is how magnetostrictive strain varies with the magnetic field. So it's kind of electrostrictive. It's kind of a quadratic effect. So for ultrasonic transducers, we want to apply bias with permanent magnets so that you have a center magnetic field so that you can go on both sides and stay in the linear range, to have a linear expansion of the material with a magnetic field.
Quick
So that,
question.
yes.
Is the magnetostriction entirely along the axis of the actuator?
Yes.
Also some
Yes.
transfers?
It is. So this is a cut cross section of the ultrasonic transducer. The magnetostrictive material, it's a giant magnetostrictive material because it gives an extra strain due to a magnetic field. It's terphenol D. terbium, and I don't know these other ones. And it's actually a conglomerate of other, yes, particles.
What's the stroke distance? Do you know the stroke distance?
I show it because I tested them. And we'll see that it's very similar to Woodward's thruster because there's this heavy tail mass, reaction mass. It has threaded output interface where I can put a dynamic mass. So any variable mass which can tune that resonance frequency. So this is like the aluminum mass at the end of Professor Woodward's. This is the actuator, and there's also kind of a spring. The flexure is also applying kind of compression. Even, yeah, it's also required by the terphenol because it's powder material sintered.
What is the application of this?
Ultrasonic. So it's provided by Etrima. We bought this from Etrima.
Cross section only 1/2 of it, so it's
yep.
symmetric?
Yeah, it's symmetric.
Okay.
Exactly. So you have, yeah, exactly. The actuator is this terphenol rod. Has low hysteresis. And it's more robust than the piezoelectric actuator because we have run a lot of tests with it and the spectrum didn't change at all. And it's available off the shelf, but it's limited in frequency. We cannot go too high with the frequency because of eddy current losses. So the higher the frequency, then the higher the losses. And so these transducers are actually only designed up to 30 kilohertz, I think.
How much money is this Etrima CU18A?
I think it was around $1,500, something like that.
1,500.
1,500.
So this is Impedance Spectrum. You guys are familiar with those now. That show two different curves. One with a 0 gram output mass, a dynamic mass, and one with a 40 gram output mass. The 40 gram output mass is here, so the resonance frequency shifts to the left, to the lower frequency as expected, but has a higher peak. Higher peak current. This is not impedance, it's a current, sorry. So at resonance we expect a surge in current. This means that with a larger mass we can increase the power that's being supplied to the magnetostrictor. So that's what we selected because then we can increase the amplitude, we can increase the power variation and hopefully create a larger mass fluctuation. And this is what you were asking about, Jamie. The displacement is shown in orange. The impedance is shown in blue. So low impedance, high amplitude. That is in micrometers. So at 20 volt amplitude, I have almost 2 micrometers.
1.6.
Yeah, 1.8. All right, so this is much bigger amplitude than the aluminum mass on the Woodward Thruster.
Which was around 0.20.
Yeah, and so we would expect a thrust if it's produced by the opposite side. If the mass fluctuation is dependent on the change in energy and in the thruster, which depends on the amplitude of vibration or the acceleration, we expect it to be much higher with the magnetostrictor because we have a similar dynamic mass.
How much bigger again than a Woodward?
15 times higher.
15 times.
At the same voltage.
What is 15 times higher?
The amplitude. And the thrust because, I also do an estimate of the thrust. I didn't put the equation here, but I estimate it to be also 15 times higher. Because
my net restrictive is 1.6 micrometers, and the mega drive is 0.2, so that's a ratio of 8.
Yeah, I don't think that was at the 0.2 you have. It's not at the same voltage. So I would have to give you the numbers.
It looks like the stroke is 1,000 times more than the Woodward device, right? They measure 13 nanometer as the maximum displacement. You're measuring 1.5 micrometers.
Yeah, but I'm trusting my measurements for the Woodward Thruster.
You'll be able to see it better.
Yeah.
That's actually good. You should be able to see it all the peak frequency.
Yep. So that's the point for the magneto stricter. Yeah, and Matthias is going to show you the thrust measurements for all of those devices, right? David, yep.
Professor Woodward says that the thrust varies as omega to the 6th power.
Yeah.
To the 4th power,
That's also based on what kind of assumption you make for how you calculate the mass fluctuation.
That's a very, very rough calculation. It's not anywhere near how we can.
But we cover all that because we test at different frequencies, we test magneto stricter, we test all of those things. And Matthias is going to present all the thrust measurements. Yes, Greg?
One thing I haven't heard too much of is any dependence on temperature for any of these devices, as far as how hot do they get when they're running, what does your model say, how hot does this magnetostrictive device get when it's operating, duration. Do you have any insight into temperature sensitivity to these things?
I can say something to that?
Yeah, you can say something while I search for the slide.
So the magnetostrictor actually can't be driven at a higher voltage than 100 volt peak.
Okay.
Even at that voltage, it is suggested to use air cooling of the thing.
Okay.
It has 2 knobs you can put compressed air into.
Oh, okay. All right.
So we only drive it at 75 volt peak and only for 20 seconds.
I see. Okay.
75
But it heats up.
Yeah, and I was wondering if there's any temperature measurements in this analysis. Unless that's something that
It's important.
In this talk and also not in mine.
Yeah, but it's important. One of my recommendations for our experiments is stricter temperature control, because it does change the spectrum. This is the red curve is the impedance of the thruster before the experiments that we do, and the blue one is after the experiments that we do. And you see, this is just an influence of the temperature, that the Q factor of the first peak, it's gone. The peak is gone. So you don't expect the same, you can't expect the same thrust if you're running the thruster for a few profiles of 20 seconds. And you also don't expect the same phase relationship. So that also affects the thrust if it's calculated this way. So what I'm saying is, if the thrust observed by Professor Woodward is constant, then maybe it's something else. Is it? All right. Last experiment. Rotary device, which was also thought by Professor Woodward, and we want to make it rotate up to 50 hertz. Does it play? It's not playing. Why are you clapping? No, I'm not finished.
Wait.
I'm not finished.
Hey.
I want to play this video.
It's 5 to 11. Just
All right.
Look at this.
So we have this metal cage, so that we don't have the effect of the charged acrylic plastic. We did observe a distortion in the accelerometer that we have. It's unfortunate that there's no sound. So basically we have
I think it provides also ballistic protection.
yes. We actually avoided, with this good design of a cage, we avoided getting shot by a projectile in this configuration. There was a very loud sound, but we were protected. How it works is that we have a stack and a counterweight so that it's balanced and we don't have eccentricity. And in that stack we have, I'm going to go back, a piezoelectric stack and transducer, or a strain gauge. And this is also clamped. It's basically like the Woodward Thruster. But this transducer picks up then the piezoelectric effect and also could get the mass fluctuation, because this mass fluctuation is accelerated by the centrifugal force. So it fulfills the conditions which were stated by Professor Woodward, that there's an acceleration and mass fluctuation producing effect, which is the piezoelectric effect from the actuator stack. And of course you would see electrostriction at twice the frequency, so the same frequency as the mass fluctuation as the one we would expect. But if we change the rotation rate, this would change the mass fluctuation, but it wouldn't change the electrostriction, provided that we drive the stack at a constant voltage. So this is how we would be able to detect the mass fluctuation. The problem with that method is that we have a very high inverse piezoelectric effect, so the extension of the actuator, compared to the electrostriction or the mass fluctuation. So we have to filter that out, the piezo effect, and then amplify the mass fluctuation. And because they're both at a very close frequency gap, you need a very high order amplifier. And if we do that analog, then it introduces a bunch of other noises that could tarnish the measurement. So we're playing, the stage that we're at is, the student has finished, it's not me, has finished building this rotation device. And we're now playing with digital filters, notch filters, to damp the piezo effect so that we can see the mass fluctuation. And this is a graph showing the accelerometer signal that does not show any significant eccentricity due to the rotation, so that's good design.
Did you try applying the centrifugal force orthogonal to the axis of your piezoelectric stack?
But then you would have an influence of gravity, right? You're saying if you're rotating it...
just rotate 90 degrees.
The whole structure, you mean?
Hmm?
You're rotating the whole structure?
No, I just mean, so the centrifugal force is oriented parallel with the plane of the actuator discs.
If you turn it sideways, it doesn't change the moment of inertia.
Okay. Well, but then the centrifugal force wouldn't push on the transducer, and we need it.
The center line of the discs with the...
Yeah, because
has to point towards the pivot.
this acceleration actually amplifies the mass fluctuation, right? The centrifugal force, or what we would detect with the strain gauge, is the force, not the mass fluctuation directly. So you need the product of the mass fluctuation times the acceleration, which is provided by the centrifugal effect, and so you actually need it to be aligned.
I just wondered if it would affect the electrostriction. You'd be acting on the lattice of the
Can we continue now? It's getting rather late. We've got 2 more students.
All right, to take home, the MET is complex and affected by the loaded system amplifier, what you connected to it. And the Q factor and resonance and the relative phase change depending on the temperature that you operated at. And of course, if there's a transformer, that would also affect the dynamics. But it's not something that we should be concerned of if we have the required voltage to drive the Woodward Thruster. It also, we expect greater thrust with a mixed signal rather than relying on electrostriction, and larger thrust with a magnetostrictor. Future work, as I've discussed, stricter temperature control and performing a spectrum at a high voltage to make sure that we nail the resonance frequency before doing the spectrum at the high voltage that we're driving at. So if we do a spectrum at a lower voltage before doing the test at a higher voltage, then we're not exactly at the same resonance frequency. But I also showed that there's a high mechanical vibration at resonance at where the impedance is minimum, and there's a higher current. So we can track the higher current in our experiment. That's how we perform the experiment. I'm going to let Matthias speak about the results of the experiment. Sorry I took so much time. This is the references.
So my name is Matthias Kößling. I also work for Professor Thalmer, and I want to talk a little bit about the thrust balance and the results we get for the Mach effect thruster and also the magnetostrictor. I would also like to thank DLR for funding this project. And by the way, I also will try to speed up my presentation a little bit so we gain a little bit more time. So I will talk first about our thrust balance, our current thrust balance, a little bit overview what new features we added to the thrust balance. Then about the cable measurement, that was a criticism about our last paper. Then the characterization of the balance, and afterwards I talk about the thrust, the Mach effect thruster. I will talk a little bit about the paper we published a few months ago. Then I go into what equipment we use, what the spectrums are, what our setup is, and then basically the results for the Mach effect thruster.
Can you pull the door closed, please?
Yeah. Afterwards, I talk about basically the same thing about the magnetostrictor, and then I show what future design, because our thrust balance is not very suited to measure Professor Woodward's thruster, a new thruster design, and what we want to do in the future. So first topic, the thrust balance. Yeah, Professor Timer already mentioned we have a concrete block below our vacuum chamber, and it's around 2.7 kilogram, but I think it did not help to damp any frequencies coming from the foundation of the building. So that's also the reason we always measure during the night, so no people are in the building. Yeah, we have a very huge vacuum chamber. And all our tests for the advanced propulsion stuff, we don't go to high vacuum, we only are around 10 to the minus 2 millibar. Huh? So the overview of our thrust, yeah. So we use a torsion pendulum, basically the same Professor Woodward uses, but we use a E20 C-flex bearing or pivot, and this is actually 8 times, had an 8-time higher spring constant than Professor Woodward's. So our conversion factor from displacement to force is worse, basically. But we choose this bearing so we can put a lot of force, a shear force on the bearing, because if we put the EM drive on the experiment box, it will apply a shear force to the bearing, and this can actually damage the pivot, and we actually damaged one previous one that could not withstand the high shear forces. For a displacement sensor we use the AtoCube IDS 3010. It measures the absolute position and has actually a resolution of 1 picometer. But the noise of the interferometer is 1 nanometer, but if you cool all the things down, the noise should approach resolution, but for us the noise is the most important thing, and it is 1 or 2 nanometer. Also, because we have this bearing, we can put a lot of weight on our balance, so we have 20 kilogram for our experiment, including the electronics. And all our communication with ducts and all this kinds of stuff happen over infrared, so no cables coming from outside on the balance. So we calibrate, like Professor said, we calibrate our balance for each test and after each test, before each test and after each test. And for this we use mainly a voice coil by this company, but we also have an electrostatic comp. A voice coil, by the way, that is just a permanent, it's just a permanent magnet that has a solenoid on the other side, and it's basically a speaker. And if you apply a certain amount of current through the solenoid, it will attract the permanent magnet. And so there are no confusions, the magnet is on our beam. So every interactions with other stuff, current that flows on the balance itself has no interference with the magnet. We also have a center motor to align the voice coil, because this only has a operation of around 2 millimeters or so, and we have to align our balance to this thing, so we use this below our thrust balance. So what it basically does is applies a torque to one of the bearings, so we can switch the zero position of the balance. Another thing Professor Woodward also uses, we have 4 liquid contact metals. We have it a little bit different because we have a grounding shield around it. So basically the copper shell around is where the ground is, and the middle is the positive thing, and all of this is filled with liquid metal, in our case gallium. And another thing we have on our balance is a motor to rotate our experiments, because it's very annoying to want to do a 180-degree test, and you have to open the vacuum chamber, turn it, pressurize it again, and so on. So we have a motor, we can do it from the outside. For damping, we use magnetic damping, basically eddy current brake. And also here, the magnet, again, is on the beam itself, so no interactions should occur. And all the cables that are outside of the balance are far away from this magnet. Yeah, I will talk about the damping a little bit later and show a measurement of that. And also we have 2 tilt motors to level the balance in the vacuum chamber. A new addition to our balance was a radio frequency feed-through, because in our previous experiments we saw that especially the amplifier heats up very much during operation, so we got huge thermal effects. And the other thing is, if you turn on the EM drive, the amplifier draws more current, and this current can produce effects with the Earth's magnetic field or other stuff in the proximity of the balance. So we wanted to remove it. We have it now outside our chamber. And to put the radio frequency still on the balance, we built this little thing. And we looked into a couple of other stuff. I know Mike McDonald uses a very precise thing, but this is, it costs not a lot, and it's basically, this is the RF pin. It's also in liquid metal, and around it is the shield of the radio frequency. So it's very similar to the coaxial liquid contact we use for DC at low frequency, but these contacts are a little bit closer, and Marcel will talk about this a little bit more. So other features, yeah, I don't think I should mention these. I mean, we have a LabJack T7. It has a bunch of analog input, output, digital stuff, and so on. And what we actually did, normally you communicate with this over Ethernet or USB, but we wrote a program so we can use it with a serial connection and then put it over our infrared communication system. Yeah, we use infrared temperature sensors, and yeah, basically we have a bigger box now to encapsulate the whole EM drive. So about the cable management, one of the criticisms was that these cables are not very optimized. They have no copper shielding around it, and here's a loose cable. But actually, all the cables were twisted the whole way, and only this small part was not shielded by a copper mesh. So in the new coaxial things, we changed it and put a proper shielding around it. So then I'm already at the characterization of the balance. So this is a typical noise level. So like Maxime already told you, we average all of our profiles to get a lower noise level, because yeah, we have a way worse spring constant than Professor Woodward, or even Jamie. I mean, Jamie has even double the resolution of Professor Woodward. We average a lot of profiles, and then we get something like this. So that's basically a noise of around 30 nanonewton. So the damping, this is our old damping, and it was a damping ratio of around 0.1, so not very good. And it's a little bit because how the damping itself was set up. So what I did is basically I increased the copper surface and opened the iron core, so I can put the copper surface inside it. And now we have a damping ratio of 0.4, and it looks basically like that. And my goal, I know a lot of people want a critical damping of 1, basically, but I don't think you need to go that high, and I try to aim for 0.7, because if you have a damping ratio of 0.7, your response goes up, goes once over your steady state, and then it reaches the steady state. So that's what I aim for. Yeah, and you see here it.
You know that JPL, Caltech had a very thorough report last year with recommendations for micro thrusters in the torsional panel. And actually they recommend to have a damping ratio of around 0.5, 0.4 like you have, and not 1.
Yeah. Yeah.
That paper also said that 0.8 was fine as well.
Yeah.
I've heard that same paper.
Yeah, like I said, I try to aim for 0.7. I could increase it still because I can put, if I go back a little bit, if you see here, this is actually the point for damping. So I could slide this copper a little bit more into the magnets to increase the damping even further. And if I have time, I will try this. And like I said, I want to aim for 0.7. Yeah.
How thick is your copper?
2 millimeters.
That's very thin.
Yeah. Yeah.
But much better low frequency, the thicker the copper.
Yeah, I know, but this damping can also be adjusted from outside the vacuum chamber, so I could technically change it during operation. But and to do this, I have a motor down here and this gear. And if the copper is thicker, then it's more weight. And if I don't have a current, because I normally, if you plug your stepper motor to a driver circuit or something, it's always under a certain amount of current. And I don't want to have current near my balance, so I have a relay to shut the complete circuit down. And then the holding torque of the motor is too low to hold a high weight there. So I can't really go and thicken the copper. Yeah. So the other thing, we saw that our laser interferometer and also our balance have an inherent drift. The laser interferometer I tested, I had a fixed position and I measured the displacement overnight, so there should have been no displacement, but there was a slight drift, so it has an inherent drift. And other drifts, if you heat up the thrusters, you get thermal events like Jamie already told you. So to look at our measurements, we have all the individual ones, and then we have a kind of procedure to remove drift from these measurements. So we use two different methods. First, we remove basically the first sector, so everything that was before the thruster turned off, we fit a plot in it and remove this from the whole thing. I show a picture in the next slide. The second thing is we do the same for the first and for the fifth, that it's after the thruster is turned off again, and connect these two lines with a straight line. So this is basically to remove thermal events. So this is what it looks like. So I have here sector 1. I fit a line in it, in this part, and I extend it obviously, and then I remove this whole line from the measurement, so I get basically here an even thing, and this, yeah, looks different. And the other method is I have here again my fit here for the last sector, and then I connect these 2 points with a straight line and removed it, and basically I can remove thermal drift.
Higher damping? Is that what the 0.43 damping?
No, that has nothing to do with the damping.
Do you have any idea what the drift is due to?
Yeah, this drift is most likely because of the balance itself or the laser interferometer, and this drift is thermal heating, basically. By the way, yeah, if you apply a current to your thruster, it will heat up. And I mean, the Woodward Thruster, we put 100 watts into it, and it's very huge power, will heat up. The way, by the way, you can do this, the thrust should respond similar to this. So it should go up, keep a straight line, and then go down again. If you have thermal drift, it will look more like a straight line. It does not look like a straight line, but you will see how thermal drifts actually look like in Marcel's presentation later. But that's how we do it. Yeah. So then the calibration of our balance. Like I said, before and after each measurement, we do a calibration. So we do basically these steps, these micronewton steps, hold them for, okay, in this picture it's actually 120 seconds. But we do a step, do a step, do a step, do a step, do a step. Calculate basically the average of this point, plot it in a line, and the slope of this line is basically our calibration factor, and for this measurement it's 6 micronewton per micrometer and has a certain standard deviation. So to verify this, I did 200 measurements with where I commanded 1 micronewton of commanded force. So this is the response. And for some reason, I'm not very certain why this is. I only get 0.9 micronewton. So I have a 10% error in my measurement. And I'm not very sure why this is. Because the calibration before and after show the same calibration factor. So it should show 1. Yeah, it's weird. This measurement is because our thrusters, we normally don't drive for 60 seconds. We only drive for 25 seconds. And our balance, because of its huge weight on the outside, has a very very high eigenfrequency. I did a test where I only had 20 seconds, 25 seconds, and you see the steady state is not even reached, and the force you see is even lower. So this has to be considered if you look at the results of the thrust balance. So now I want to talk about our paper we did in Sevilla at the Space Propulsion Conference a few months back. And basically what this paper was about is what our results of Professor Woodward's thruster. So here again you see basically the spectrum you already saw from Maxime. I prefer always to put the current as a way to see the eigenfrequencies. The Q values, they are not very high, but okay. So this is the result. For the 0 degree measurement, we see a force, a deflection goes in this direction. Everything looks fine. And this is, by the way, with only 75 volt peak and at 31 kilohertz.
Sorry, what is the scale? What is the scale?
This scale?
Yes.
The top one is 800 nanonewton. So this 800 nanonewton. And this is actually around 600 nanonewton force. And a noise of, maybe 200 nanonewton. So, looks good. We turned our thruster around 180 degrees, did the same test again, same voltage, everything the same. The thrust flipped on the other side, same value, everything looks good. Then we did a 90 degree measurement, so we should see no force. Yeah, looks good. And then what we did, here we actually turned the box. So all the cables in the box rotated with the box. Then here we only rotated the thruster. So we opened the vacuum chamber and only flipped the thruster on our setting, not the box. So the cables were the same as in this measurement, basically. Only the thruster was flipped. And we saw the thrust is in the same direction as 0 degree. So that is bad. There's no actual thrust there. It's an artifact, most likely current. So, the force shows in the same direction. So then, this is not in the paper, but we did these measurements with a transformer, with our transformer, not with Professor Woodward's. It's basically how our amplifier is set up, and I will talk about.
Accounts for why the device looks so shiny.
What do you mean?
It wasn't so shiny when it was returned.
Okay. I show a picture of that later. I will talk about our amplifier a little bit later, but anyway, here we did 140 volt with the transformer. So this is basically the reference. I changed the amplitude here a little bit, so the top one is 2.5 micronewton this time. And 0 degree, it looks basically good. Yeah, the amplitude increases, but if you see, this is a little bit wobbly. And this is straight, and it goes basically straight down. So it looks very similar to a thermal effect. But anyway, the voltage is increased, so the amplitude should also increase. So basically it looks good. Then the 180 degree, it flipped, that's good. But the amplitude is a little bit higher, but not really as high as this one, so not very good. And the 90 degree shows basically the same result as the 180 degree. So also not good.
You mentioned thermal effects. How hot did the device get?
I can talk about how hot it got a little bit later. We measured the temperature, but I don't have it here, but it got hot. I can say a little bit later something about that.
Thank you.
So basically the thrust does not increase with higher voltage and the transformer. That's what this is saying. So then we did a mixed signal, like Maxime said. If you don't drive it with a pure sine, but with a combination of two frequencies in a sine, you should get much higher force response because you can use the second harmonic, the piezo effect there. So this is again the reference, yeah, the amplitude is again 800 nanonewtons. So 0 degree, it looks in the same direction, but it's not increased, so bad. 180 degree shows in the opposite direction, but also not increased, bad. And 90 degree, okay, it basically shows nothing. Noise is a little bit huge, but that's okay. But what this basically says is the mix does not increase the signal. I have to mention the voltage is a little bit lower because if you add two sines with this voltage as an amplitude, your max amplitude actually is double that. Because if the sines overlap in a certain way, you get double the amplitude. So, yeah.
Actually, it looks to me like you're not really seeing the little effect because I'm not seeing the little transients we switch on and off.
Yeah, the transients we don't see.
Yeah, you should be seeing them.
Our balance is much more heavy.
Yeah.
It's very heavy.
Yeah, so it's much more heavy.
And the response time of our balance is way higher than yours, so we
What should you see transients? What is the origin of the transients?
PPT, rate of change of power. You switch on, you switch off in opposite directions.
So basically what you would see is something like bep, bep.
Yeah.
But we don't see this. Actually, in a previous balance that had not such a huge weight on all the sides, we saw these transients, but now we don't see them. And also, Jamie tried to simulate your setup, your balance, and all these kinds of stuff. And our setup looks a little bit more complicated. There are more connections there. I show a picture later, so maybe we can't even see them. So, but yeah. But anyway, mix does not increase the signal. So then we did one test with a new amplifier and we got up to 180 volts peak. So again, this is the reference. And I also have to mention we added a heatsink to our thruster. So basically we put our thruster on a 250 gram copper block. And that's the result. So the current is a little bit higher, but basically no result. Bad. So voltage is doubled, the thrust is decreased, most likely because we put the heatsink in.
Do you have a diagram of what that looks like?
I have a picture a little bit later because I don't have it here. I have it for our setup, but it basically looks the same as Professor Woodward's test.
And you ran to 31 kilohertz, which isn't the 36 kilohertz that we ran at.
Yeah, but you use the transformer from the get-go, and this shifts the frequency a little bit. If you
You're running it right on resonance, which means
yeah, if you look here, it's basically we tried to get into this.
We can really track that we are on resonance during the thrust measurement.
Yeah, I want to talk this a little bit later. That's just a recap. So what were the results of the paper? So, and I said this was the last test because here I can say the temperature of the thing reached very high temperatures because one of the leads got loose. And actually we did a test. We did a test before that one where we did not have this copper block but a piece of plastic as a mount because we had to isolate it from the balance ground because how our amplifier works, and we actually melted that piece of plastic. So yeah, that was the last test, and then we sent it back to Professor Woodward. So basically the conclusions from this paper and these tests are our spectrum changed during the test. That was what Maxime basically said. But the thrust flipped if we flipped the box, but that not flip if we only flip the thruster. So that's a contradiction. So there was no thrust there.
I've done that test too. I've taken the thruster and flipped it inside our box and mine reversed like it.
Okay.
Maybe you've got a bigger box. I've done the same test and mine reversed, like it normally would. I guess my leads are a lot smaller than maybe you do.
Yeah.
I think the leads do.
Yeah, we have to address a few things with our test, but I talk about this a little bit later. So basically, transformer higher voltages also showed no significant increase in thrust. The mix signal had also no significant effect on the thing, but we expected 1,000 times greater thrust results, so that did not happen. And when we put the heatsink in and even got to higher voltages, the thrust vanished completely. So now to our thruster. So I will talk a little bit about our equipment. So these are basically waveform generators and an oscilloscope we use to measure current and voltage and apply the frequencies we want to test the thruster at. And this is our amplifier. We use an Apex PA04. I mentioned this last year too. This is an amplifier made for piezoelectric materials, stacks especially. And this can output up to 100 volts peak, one of them. So we have basically two boxes. We have one box that can output, that has only one amplifier and can output 160 volt peak. It's a little bit less than the actual specification, but we could go a little bit higher, but we don't want to go with that box. The second box, we use two amplifiers and use them in bridge mode. I think that's very similar what David Jenkins does with his. Your D-class amplifier also is in bridge mode, right? So you have double the voltage. And we can go up to 360 volt peak there, and that's basically the picture. In this box there's a preamplifier and some filters to smoothen the signal.
What is the load resistance these amplifiers want to see?
I don't know. I don't know.
What is the power rating?
What do you mean by power rating? How much power they can output?
Power out of one amplifier.
200 watts.
What wattage? What wattage?
Watts? 200.
200 watts?
Yeah.
Oh, okay.
Yeah. And at 100 volt peak. And if you don't want that high of a voltage, you can go up to 20 amps, about 200 watts. Yeah. So because we have the second amplifier box, we don't need a transformer to get to higher voltages. That's basically because Maxime already told you that transformer can have significant impact on the spectrum and how your mechanical and electrical resonance occur. So we had to calibrate these amplifiers because when we did the first test and tried to measure a resistance, we got not the results we wanted. So basically what we did, we took 80 ohm resistor, 100 watt power rating, and we commanded a fixed voltage and did basically a sweep. And we got this result. So basically this is the voltage we measured with an oscilloscope, the black one. And on the right side is what the box gave us as a result. And you see there's a discrepancy, I mean, yeah. And we did the same thing for the current. And then we got an equation basically from that, put it into our program, and then measured the current, the resistor again, and we got a nice 80 ohm resistance for the first box and also for the second box. So that's basically how we calibrated our two boxes, so we know they output the right thing. And now to our thruster. So the spectrum you already saw from Maxime with the frequencies. These changed during the tests a little bit, but we mostly focused on the second peak, this one, and the fourth peak, this one. So basically 37 and 72 kilohertz. That's the electrical setup. This is basically the supply voltage for the amplifiers, yeah. And here you see where the limit of the 36 volt come into play. If you would increase that, the amplifier would see a higher supply voltage and could be damaged. So we want to stay a little bit below so we don't destroy our amplifiers. Here we have our frequency generator. We measure the current and the voltage. The signal goes through a coaxial liquid contact on the balance and then to the thruster. This is the mechanical setup. So we have the thruster put basically in one of our mu metal shielded boxes in the middle. It's mounted on a copper plate as a heatsink, and also on a peak plate, because again, if you have an amplifier that is in bridge mode, you don't really have a second ground there. It's a different signal, and because the Woodward Thruster, the bracket is basically on the same potential as this side of the PCT stack, and the amplifier is not ground, you would have a short there and would draw huge currents. So we had to isolate it electrically from the balance, basically. These are temperature measurements, and yeah. So, because if the thruster heats up, the frequency of the thruster changes, we have a tracker that tracks basically the frequency and changes the frequency according to it. And you can do two main approaches there. The first is you just track the maximum current, so you always go in the direction where the current is maximized. And the second thing is you just want the phase to be 0. That's not actually the right thing, because you saw at the resonance the phase is not really 0. But if you want the phase to be 0, you can track that. And the phase, to track the phase is actually much more easy, because if you don't use the absolute value of the phase, you always get the direction in which frequency direction you should go. If you have a negative phase, you have to increase the frequency, and if you are a positive phase, you have to lower the frequency. So we basically only used the current tracker because we wanted to put as much power into the thruster. And there's another problem of how we do things, because we do 200 profiles over one night. And the tracking frequency of the last profile is not necessarily the starting frequency of the second profile, or the continued profile. So you can do either way, restart the tracker completely and start from the point you figured out during the spectrum. You do a quick spectrum and set the tracker to the actual frequency you measured there, or you just ignore that and start at the same frequency. So, now to the results. We did 180 volts, and that's basically the first peak. The frequency changed here a little bit to 37 because, yeah, it just changed. So, 0 degree, no force, not good. 180 degree, we see a small force, but it's way smaller than what we saw with Professor Woodward's thruster. And also the direction of the thrust of the 180 degree flipped. Previously it went up, now it went down. So that's not very convincing. And if you subtract both of them, you get no net force at all. So basically there's no force there. So the second thing, we got to the second peak. You can put much more current in there. And also your frequency dependence on the force should increase the thrust immensely. So this again, the reference. 0 degree, again, nothing. And that's 180 degree. I think here happened something weird, because I don't actually have the current measurement, because I forgot something to set up in the measurement. But you see a much higher response. And here you actually see the transients that Professor Woodward measures. But I'm not very sure that this is actually the thrust. So I say that's also not a good measurement, because it also doesn't comply with the 0 degree. So then we did two other tests. We had the voltage lowered a little bit and did it at 180 degree. Again, at 180 degree, the force went down first, now it went in the opposite direction. And it basically has the same amplitude, so it's not very a good measurement. The second one, the mixed signal, again, we would expect a much higher force there, but we actually see, again, nothing. So the conclusion?
This is all mounted on that copper plate?
Yeah, all with heatsink. So basically what we saw, our spectrum is different from Professor Woodward's thruster, so it's maybe not really comparable. But we did a similar voltage range of Professor Woodward, and basically we saw no force with our noise of 50 nanonewton. Also, the frequency increase did not increase the measurement. Like I said, the 180 degree measurement is most likely in error. And if I halved the voltage, the thrust direction flipped again, so again, a contradiction, and the mixed signal showed no force at all. So now for the magnetostrictor.
A quick question, did you test your device without the copper plate?
No.
Okay.
Yeah, maybe we should do that. We also did never test again only the flip thruster.
Yeah.
That's maybe also something we have to do. Because like I showed you, the first result of Professor Woodward was very promising, but only if we flipped the thruster we saw that there's no actual force. It was probably a current effect. So, magnetostrictor, this is a real picture, and again the spectrum, where the frequency is around 9.6 kilohertz, has a very low Q factor and this mass. And like I said before, the voltage you can maximal apply to the thruster is only 100 volts. So we kept a little bit below this, so we don't overheat it. And also the frequency is limited to 30 kilohertz, like Maxime already said. So this is basically the setup. Also, we put it on the copper plate to remove potential thermal effects, have again our temperature measurement set up. And this thing also has no rubber between anything, so it's pure on the belt.
In the magnetostrictor, where is this place where that is responsible for the very low Q? Where is you think the highest internal dissipation? Where is the most damping within that?
In the terminal rod, that's where you have any current losses.
Thank you.
That makes sense. And maybe something to add, the temperature measurement that you see there, this is an infrared sensor, so it directly measures the temperature at the actuator.
Yeah. So it's basically non-contact temperature measurement. So, first measurement, 0 degree. 0 degrees. So we see a force. It also shows in the same direction as Professor Woodward's thruster. And yeah, we see a turning off thing. Balance does not go in its original state. But we can say, yeah, it's okay. 180 degree. We get basically the same measurement. So not very good. 90 degree. Yeah, you could argue that this is 0. So I checked it as positive. But if you subtract both of them, you don't get a net force, so there's no force there. But actually, during the sign, Maxime forgot to mention that, but because you have no electrorestriction in this material, with a sign you should not see a force anyway. So actually this is good that there's no force there.
Sorry, could you repeat this last point?
The magnetostrictor, because it is not a piezoelectric material, it has no electrorestriction, and if you only apply a sine wave, you don't have the benefit of excite the second harmonic where the electrorestriction is. Basically what Professor Woodward does.
So we have to drive it with a mixed.
Yeah. So this can only be used with a mixed signal. So that's basically, yeah, we did half voltage. The signal vanished, and if you look closely, the current is around 2 amps in these measurements, so it's very huge. So if you calculate the power, it's around 100 watts. And if you halve the voltage, you also halve, obviously, the current, and the signal vanished. So no force there. And if you use a mixed signal where we should see a force, a way higher force than for the Woodward thruster, and yeah, we see no force. But again, the current is very low in this measurement. So what we think happened here is it's just a current effect basically. So what we did is we used a bunch of resistors to get basically an impedance where we could use the same voltage and get the same current. So we put it on the balance and we basically see the same result. So the thing you see here is just a current measurement, so no force there. Basically the conclusion. So because our balance is very heavy, and the spring constant is not that good, we want to build a smaller balance that resembles more Professor Woodward's balance, basically. So there we use an A20 and an A30, and these are, I forgot the numbers, but I think they are a factor 2 better in spring constant. We use the other stuff is very similar. We use eddy current damping. The experiment box can rotate it, but with a much smaller motor. We only have 2 coax liquid contacts, and we will also use a voice coil. A little bit a different one, because in this measurement we don't have this center motor where we can align the voice coil where it's supposed to be. So we use a voice coil that has 6 millimeter range. So we have to set it up a little bit more careful. And for all the data acquisition and so on, we use this time a LabJack T4. It's basically the same, but it has a few fewer analog inputs and so on, and it's smaller. So what I did was I tried to estimate the calibration factor for this. So for the A20 we get 0.2, so it would be a factor of 10 better to the current spring. And with the A30 we get basically the same as the current balance. But for the response time, again here we have a better resolution, but basically it's not really the response time, it's the period, but the response time and the period correlate in a certain way. So basically the response time is the same, but the resolution is better, and here the resolution is the same, but the response time is better. So that's what we want to try there. And we can easily exchange these 2 bearings in the balance, because they have the same diameter. So basically our future tests, we actually did a frequency sweep, but because of our balance has a very slow response time, we could use it for any reasonable thing. So that's what we want to do with the new balance. We also want to design a specific transformer so we can replicate Professor Woodward's, because the only transformers we have from...
You don't expect us to send you another piece of apparatus.
Because the only transformers we have from Professor Woodward, and that's the reason we thought we never got any, we can't actually use with our amplifier, because the input impedance of the transformer is so low that our amplifier, the voltage would not be there. The current is not enough from our amplifiers. But like Maxime said, is it really necessary? But yeah, maybe we do this. Then we redo all the tests with our smaller balance and try to increase the voltage of our mix signal. And obviously we have to solve our electric current problem. The current problem is maybe because when the workshop manufactured our the version 5 balance, there was a mistake made. The machinist read the measurement wrong. So the mu metal shield that's actually inside the beam does not fit exactly in. There's a 2 millimeter gap or so. So that's where electrostatic field can go out and cause problems. And that's basically my presentation.
My topic is actual progress. I've got enough time? Okay, I've got enough time. Actual progress on the M drive testing it with Technical University of Dresden. And I will talk about this content. I will repeat or shortly show our past results I also presented last year. I will talk about some common questions from another spaceflight forum. I will show some hints from Roger Scheuer himself. And after this, I will go to our new setup. I will talk about the hardware recalibration I did and our measurement results. I do a short conclusion on our new setup, and then perhaps I show some problems in our future plans. Well, perhaps you all remember the setting from last year. We used a handmade, hand-pressed copper cavity built after the design of another geometry. But I have to remind, this geometry suffers from manufacturing tolerances. We are suffering from bending radii. We've got a movable or adjustable end cap, so the geometry isn't not the same as another geometry exactly. Well, we are using coaxial RF components for power input and power output reflection. So we are doing our frequency tracking with this way. We are still not using, or we did not use, a sensing antenna inside of the cavity in this configuration. we used the already mentioned 50 watts amplifier over the cavity itself, and this was also placed inside the vacuum chamber. So we had massive thermal problems or thermal issues. So we were just able to power our amplifier with about 2 watts in a very short time to avoid thermal overheating. Well, as you can see on the picture, we didn't use a proper magnetic or shielding in any way, and we observed or we used DC currents for amplifier supply on this balance, so which could be a problem I mentioned later. Well, these are the calibration tables of our last cavity. Here you see the unmatched S11 frequency sweep done with our VNA. The antenna, I have to mention, the antenna at this time was designed for a frequency about 2 GHz. And with this 2 GHz designed loop antenna, we saw these reflection peaks with power peaks at the unmatched cavity. We decided to start with just the first frequency we saw, which was 1863 megahertz, which is obviously not the best Q of these all frequencies, but we have decided to start at any point. So I tuned with cavity with our three-step tuner. You can here see the often asked for Smith chart. The matched frequency at 1863 is exactly hitting the 50, not exactly, but almost exactly hitting the 50 ohm point. And as a result of this matching, we can see a power spectrum done on the balance. So you could say, here you can see the unloaded Q factor if you want to calculate it. And from this power reflection minima, you could calculate your loaded Q factor.
What are the mode shapes that correspond to those frequency peaks?
What do you mean?
The mode shapes.
Mode shapes, I don't really know. We weren't able to measure it via infrared, and we did some simulations about it, but because of our geometry of a cavity, which is not exactly reconstructible in the simulation, we can't exactly say which mode is which frequency with our cavity. Well, these are results, or the past results from our first measurements we did last year. We can see on the upper slide our 0 degree measurement, which means in the top view our cavity shows in the right direction from the balance. We used 2 times 21s each 30 seconds, and because of a massive heating we had to cool down it 4 hours between those 2 runs. We measured in vacuum, and we implemented, or we could power in with 2 watts on the frequency of these 1863 megahertz, and we used the frequency tracker to stay on the frequency even if a cavity expands due to thermal warming or something else. In this case, we indeed saw force of about 4 micronewtons with an amplifier current of 2.5 amps. We rotated our experimental box, so the cavity showed in the other direction. We repeated the experiment. We also did 2 runs with 2 sets of 21s each 30 seconds with a 4 hours cooldown time. Also in vacuum, also 2 watts with the same frequency and same frequency tracking. And we even saw a peak, not that fine peak, but a peak with about 6 micronewtons of force. We did our reference measurements. We turned our cavity to a 90 degree direction. We repeated the experiment, we repeated the measurement runs, and we also saw force in this direction, as the sketch shows, with a size of order of 5 micronewtons, in the same direction as the 180 degree measurement showed.
Excuse me, can you go back to the other one?
Which one?
How did you get that first? That makes no sense at all. I would have assumed it would have gone left or right.
What
up and down, the thrust.
Of course it does not make sense. That's a problem. That's the point.
I just want to check. That's
we could argue.
keep everybody
Okay.
honest.
we could argue that the emitter antenna is not exactly in the center of a cavity. The emitter antenna is at the side of a cavity, so we get perhaps asymmetric.
Well, if it happens in that run, how come it doesn't have with different thrusts in other directions instead of going up and down?
Who knows? I didn't understand your question, right? Well, let me assume.
Okay.
What I wanted to say is, perhaps we could explain this thrust direction with asymmetric wave behavior inside of a cavity, but the next measurement with our 40 dB attenuator between our cavity and our amplifier also showed a force up to 5 micronewton also in this direction of the 0 degree measurement. And with this 40 dB attenuator, we can clearly say that there should be no power, should be no power inside of the cavity at all. So the force we can see cannot be caused by the cavity itself. Your question?
One of the things we mentioned when you published was that when you rotate your cavity, a lot of your wiring and your amplifier sits on top.
Yes.
So would you rotate the amplifier or would you move the amplifier?
Everything was rotated. Everything was
rotated at once.
Right.
So you didn't want to isolate the cavity or just rotate the cavity and move the amplifier off?
In the next steps. This was just the first results, the first measurements we ever did.
I guess my question is, I don't understand how you get the resonance in that direction. That's the only reason I'm raising the question.
Resonance in this direction? Resonance doesn't have anything to do with the direction.
Your microwaves. It's going to go this way or that way. I don't know why it's going up and down.
No, this picture just shows the top side view of our balance. This is the balance. This is the electronic box. This is the experimental box, which is built onto our cavity in this way. Here you can see the beam of our balance. The electronic box would be here, and this is the experimental box which can be rotated. Does this answer your question?
You got to forgive me. I'm half deaf, and you're talking very fast, so very low. So please.
Okay, no problem.
Bear patience on my ignorance.
Okay, let's resume. Well, okay. Past results summarize. The first measurement, the first direction 0 degree measurement, showed a force in the direction we would expect in the size of order S is likely as Vanessa did, and this would be very nice and look very good. The change direction 180 degrees also did what it should do, and we also were very happy to see this. We were a bit disappointed about the 90 degree measurement, but this could be explained, as I already said, perhaps in the asymmetric behavior of a cavity. But the next measurement with our 40 dB attenuation clearly indicates that the force cannot be caused by power in the cavity. Last year we concluded that these forces should be or could be explained by Lorentz forces from the DC wiring interacting with, for example, the Earth magnetic field. In our paper we published the statement, and we talked about the possibility that even some centimeters of wiring, not really shielded, with 2 amps of current, would produce a force of about 3, 4, 5 micronewtons at the location of Central Europe because of the inclination and the strength of the magnetic field on our local position. Well, lesson learned from these first measurements. We clearly have to avoid DC on our balance. So we need a better shielding, and we have to be aware of that, of course. We have to use more power in our cavity. We have to do longer runs to cope with the inertial mass of a balance, which is very high because my EM drive is very heavy. We have to be aware of the terminal expansion of a cavity if there's enough power inside of the cavity, because the center of gravity shifts, and so we could get some false results. And we have to be aware of a resonance shift of a frequency, so we have to use a tracker, which probably, yes, we have to stay at our principle of using a tracker. Well, and perhaps we have to understand better our RF behavior inside the cavity. For example, there were some measurements, some power spectra, where the reflected power, power which was reflected from the cavity back to the system, was even higher than the power we got into the cavity, measured by power meters at a bidirectional coupler. I'll come to that later. Well, let's talk about some of the common questions from our NASA Spaceflight Forum, which were addressed very often. One point was we're matching from antenna, matching off antenna to our cavity. As I already said, in these first trials, I matched my antenna, or I designed my antenna for a certain range of 2 gigahertz, and although it was designed for 2 gigahertz and the reflection peak at 2 gigahertz, it also radiated at 1.8 or 2.2 gigahertz. Of course, it would not radiate that much power at upper frequencies, but it would radiate. So I think using antenna which is not perfectly matched for the first test wouldn't be that big problem. Well, in the way of designing my cavity or tuning my cavity, I assembled this cavity. I assembled it during measuring with my vector network analyzer, and opening with an open cavity, so to say with a horn antenna, I saw just the tune frequency of the antenna, and closing my cavity, so assembling the last part of the last flat end cap of this cavity with resonance frequency of the antenna disappeared, and I just saw the resonance frequencies of a cavity. Well, talking about antenna orientation, yes, of course, a magnetic loop antenna is most likely to excite magnetic fields, and if you want to excite certain modes, it would be very good to orientate and place the antenna in the right direction and the right position. But antennas, especially if they're handmade, are not that exactly and not that precise. So also a loop antenna orientated for, let's say, a mode TE012 or so, could excite a mode TM212 if we hit the right frequency. It wouldn't be that perfect, the Q factor wouldn't be that good, but we could excite other modes also. Well, the problem of inside cavity sensor antenna, we are still figuring this out, and we still don't use it, but this will be coming soon. Well, now a nice point for José. I talked about very high Q factors last year, and also at my youngest measurements I saw quite high Q factors of about 200,000 or something, and I was criticized very often for that, so I checked it very often and very deeply, and I can surely say it's not a problem of interpolation of my network analyzer. I'm now investigating the problem of sweep time of my NVA versus the response time of a cavity. Perhaps there's a problem of a too fast sweep for the power distribution inside of the cavity and the power reflection behavior. I still don't know. I'm just investigating this problem.
How fast were you sweeping the VNA?
Oh my God, I can't say it. It's the standard setup for the device, and I just can't change it. I asked the manufacturer, and they just said, "Oh, you can do more averaging, you can do oftener sweep, but you can't change the sweep time itself."
Yeah, I can't believe you'd see a problem, but I don't know what the sweep time is.
Yeah.
What is the purpose of an additional antenna inside?
There was the idea that you could figure out finding the right resonance frequency. If you have an antenna at the calculated position and you see a field maximum at this position, you would know that your excited mode has had its maximum at exactly this point, which would be calculated before.
So is it for mode identification?
Pardon?
Is it for mode identification?
It would be for mode identification used, yes. But I'm not very convinced about the principle. Do you want to say something, Jamie? I know you've got good insights on this. Well, okay, it's too fast. Modes in their position, it's the same problem of inside cavity sensing antenna. And I already talked about the manufacturing tolerances of our cavity. I talked about the bending radii of our cavity, and also this movable small end cap. And so we just don't have another cavity to measure it. We just have our own cavity built after another dimensions, but it is not the same cavity. Well, another point was someone mentioned that it could be possible to rotate all our balance, all our experimental setup, to avoid this problem of magnetic field interaction. Well, let's consider the inclination of the Earth's magnetic field at, let's say, Central Europe or California. I think in this region it would be even the same size of order. We have an inclination of 63 degrees. at Central Europe. Let's say we are 65 here or so. That means the Earth's magnetic field enter the Earth's surface in this direction. So if we have a look at the Lorentz force, we need our current, for example, on the balance beam. We need our magnetic field, which would be shown in this direction, for example, and then we have our Lorentz force. Now let's rotate our balance. We rotate all the beam, all the wires, so we just are rotating the direction of the force. So changing the orientation of our experiment setting would not really change a power which would be measured. We could change it in a size of order factor 0.9 because the sine of 70 degrees is about 0.9 at least. So it wouldn't solve the problem at all. Well, another point was the critique that I excited resonant coupling instead of a resonant cavity, resonant mode of my cavity. Well, and so in this way I just heated my antenna. Well, I just can't say that is not the case. I'm not very convinced that it's not possible, but
the easiest way to test for that is just while in resonance, just push on your cavity, and if you see the resonance frequency move.
Right. Another way to test it is open your cavity, looking at the frequency you want to look at, and if the frequency disappears, it was a resonant frequency of a cavity. I did this, and I used such frequencies. So, who knows? Another point just mentioned was the problem of RF leaking. We did some measurement, let's say calibration tests outside of our vacuum chamber, and we did of course our measurements inside of our vacuum chamber. Low power measurements did not show any leakage at all outside of a vacuum chamber. Higher power levels instead showed a weak leakage. We used to detect this two kinds of power meter, electro smog meters, let's say it. A very fine-tuned one with up to 2000 microwatts per square meter, and a very strong one with about 2 milliwatts per square centimeter. So we've got a huge range of RF power scanners to look at our cavity, and as I already said, we saw a quite weak radiation from our cavity. A very nice point, which I will come later, is that the opening of our Mu metal shielding indeed showed a weak radiation, but also in this case of weak radiation, by opening our Mu metal shielding box, improved the resonance behavior of our cavity. I'll come to it later. Well, yes. Last summer we were visited by Roger Scheuer himself, and he gave us some very exciting and for me very important hints, especially for RF engineering and RF design. About the physical backgrounds, please contact Professor Timer. He understood it better than me, I hope. And well, there are here some hints he did. The first hint, and perhaps the most important, is that below cutoff frequency there won't be any propagating waves inside a cavity, a hollow wave cavity or something like that. So for the NASA geometry, the NASA dimensions, no frequency under 2300 megahertz should do any effect at all. We also talked about the problem of antenna matching and antenna position. I want to repeat this now. Roger Scheuer himself mentioned that spherical end caps, using spherical end caps instead of flat or straight end caps, would improve the Q factor because the phase noise would be decreased, but also straight end caps would do the job. Mr. Scheuer also mentioned that, I made some notices, that modes are probably not really the most important thing for seeing force producing thrust, and also that the HDPE, so the dielectrica the NASA used, also was not that important for producing thrust, or let's say it honest, it wouldn't do any difference, it wouldn't do anything in it. Well, and another important hint, two other important hints Roger Scheuer gave: don't trust your bidirectional coupler. I'll show it later. And the next important was don't drill yourself or don't blind yourself with the microwave power. So now we are using our device in our vacuum chamber and we have no radiation at all. Well, this is our new setup. The last year we did use all our hardware inside of a vacuum chamber. Now we are using Regal DSG 830 for frequency generating and the first, let's say, power leveling. After this, we use our amplifier we did already use last year with 50 watts amplifier RF1164. We are using a circulator to to prevent damage on our amplifier from reflected power. An attenuator at our circulator with a power meter shows the reflected power coming back from our vacuum chamber. We are using a coaxial SMA feed-through from a company is Hositrot, I think, which goes inside our vacuum chamber when from the static part of the chamber to the moving part of the balance with our coaxial Galveston feed-through Matthias mentioned. I will come to it some seconds. Going to our bidirectional coupler, measuring power input and measuring power output, so reflected power coming back from the cavity, a three-stub tuner, and our cavity with emitter antenna inside. On our balance, of course. As I already mentioned, our frequency generator is a Regal DSG 830. We have a frequency range now of 9 kHz to 3 GHz, so I can deliver all frequencies to my amplifier. We have power control from -110 to 13 dBm, so we can use the whole power range of my amplifier. This frequency generator has a resolution of 0.01 Hertz. It can be remote controlled and is now at the moment implemented in the control software of our balance. The amplifier is, as I already said, now outside of our vacuum chamber. It's now air cooled, and so we can use it with much high power levels. We can use the whole, all its power for several minutes at once, in comparison to, let's say, 2 watts for some seconds in our vacuum configuration. The DC on our balance is now just 2.0 amps for powering our power meters, with 2 power meters, compared to our more than 2 amps of power in the old configuration with amplifier on the balance. You can see here a photo of our balance with a mu metal shielding, and on the top where is our RF feed-through. Well, let's start with the SMA feed-through to our vacuum chamber. It's commercial off the shelf. It has a damping loss about 3 dB, and well, yeah, that's it. More interesting is our coaxial Galveston feed-through. In the first step, I wanted to just buy a rotary joint, which was commercial off the shelf, which would be very cheap, which would be very small, very lightweight. But rotary joints have a problem of a torque of about 0.05 Newton meters, and this is way too much for measuring our low thrust or low power, low force levels. So we had to think about something different. So we thought about the solution of the TU Delft, large copper cavity, hollow waveguide with movable end caps for getting power inside of on the balance. But we didn't have enough space and mass budget for this device, so we had to think about something very small, very lightweight, and as efficient as possible. So Matthias came to the idea just to try to connect 2 N-type connectors with some copper shielded or some, what's the material, Matthias?
Copper.
Not the copper, the plastics? PEEK, with some PEEK elements, and building 2 reservoirs for the shielding, for the ground, and a second reservoir for our, let's say, the power line. So we have just used 2 N-type connectors, positioned them face to each other very closely and rotatable. Well, the power behavior of this thing is, well, it looked very, very good at the beginning, and it looked very nice. We had damping up to 4 dB, and the radiation was very low if we also used the Galveston, yes, for the ground reservoir. We also tried what happens if we just use the Galveston for the ground and don't use a direct coupling for the power line, And we also tried to figure out what happens if you use Gallinstan inside of N-type connectors and no ground connection. Well, the problem of these two feed-throughs results in with strange behavior. We now see on our balance on our power meters on the three-directional coupler, on the bidirectional coupler, like a power oscillation on our experimental setup. For example, we used a 1 watt power input, and we saw the red line is the power input in direction of a cavity, the blue line is the power reflected from the cavity, and the gray line would be the power reflected from the overall chamber back to our amplifier. Yes?
Actually, one other question about your previous slide. Do you have an SMA feed through to the vacuum chamber?
Yes.
They're quite physically small. Do you have problems
Yes.
putting that much power through that small of a center?
The power for SMA is about 100 watts, and N-type connectors are rated for 150, I think. So the problem is not the real maximal power of SMA feed-through, but the problem is more or less really with strange behavior I will come to later. Well, most of the power of the all frequency range shows with wavy behavior, and it shows with power minimum at the power maximum of an input and power minimum at the reflected powers. And in some cases we also see these nice spots, these nice peaks between our very clearly strange power behavior. And I was able to identify these peaks as resonant peaks of a cavity. I hope which were resonant peaks. So, yes, this made some very bad headache. I come to it some seconds later. As I already said, we are using our Moon metal shielded boxes, and I'm now manually tuning our emitting antennas inside the cavity to the wished frequencies we are using as the resonance frequencies for our cavity in the measurement runs. So now our emitter antennas are really matched to our resonance frequencies of our cavity. I have to mention that we are using a loop antenna as we now did, for example, as we did in our last experiments, but now also are helix antennas. The reason is a bit, it's easy. I wasn't able to manage to build a loop antenna for a higher frequency than 2 GHz. All my attempts to build a loop antenna higher for 2 GHz resulted in smaller loop antennas getting smaller, smaller, and smaller, and we also showed 1.9, 1.8, 1.7. Today I think it's a problem of my N-type coupler, which is the basic of my loop antenna, and the geometry of the N-type coupler and the capacitive behavior doesn't allow me reaching higher frequencies with this N-type coupler. Well, so to say, the combination of our vacuum chamber, our balance, and our overall EM drive setting represents now a very, very more complex RF system as our last setup was. And I'm aware, or I recognize perhaps strongly capacitive side effects at the moment. So I identified, let's call it 4 operational cases so far. We've got one case which is quite normal and quite usable. We see up to 1/3 of our generated power at the power meter at the input side, which is quite good. We also see reflected powers which are significant and bigger than 0, and we are quite plausible. So in this configuration, in this case, we can see the loss and the reflection behavior of all my components, and at least it makes sense. The next case, which is more ideal, which was achieved by just turning our experimental box 180 degrees. It was just found by incidence, that we could input up to 70% of our generated power, and we also saw a very, very low level of reflected power. Today I think it's a very lucky case that all the waves inside of our system interfered and laid at these positions, that the 0 lines of our electromagnetic waves were exactly at the position of our critical, let's call it critical components. So if we have, for example, our feed-through, and the wave has 0 zero line crossing at the critical component, the power will go through this component without being damped or without reflection. Well, the two less nice operational cases frustrated me the last days, weeks and hours. It was, in the most cases, it was just able to get less than 10% of our generated power inside of our cavity. We saw sometimes also zero power reflection. So our reflected power from the cavity was also very close to zero. Reflected power from our chamber to our amplifier was a bit more than zero, was 1 or 2 watts, or perhaps a third of the generated power. But I couldn't figure out where the power goes. So perhaps I think about massive losses in the system. Perhaps we have some current loops, radio frequency loops, capacitive coupling to our mu metal shielding. At the moment I don't really know what it is. Another case, not that bad but also astonishing, was with high power case. We generated, let's say, 10 watts of power and we measured about 20 or 30 watts of power at my power meter at the input to the cavity. Well, I know that my power meter, that my amplifier only produces the power I am commanding. So where comes the power from? Nowadays I think it's just the problem of very lucky overlaying of my EM waves inside my oscillating system, so that exactly at the point of my power meter in, at my bidirectional coupler, the waves are adding their power to each other and the power meter just sees with sum of power. Well, that's the thing I think Roger Scheuer said, don't trust your bidirectional coupler. Well, the problem with all these cases just was that with slightest change in our setting, let's say you lift up the cover of our mu metal box, you move it 1 centimeter in any direction, they change the whole power managing totally. From a situation where a third or half of the power got inside our cavity to the case where not even 10% of power got in, was just 2 centimeters of pushing our cover in any direction. Turning the box did change our power management totally. And it wasn't able to replicate, it was very difficult to replicate any measurement or to predict what happens if we will perhaps change the position of any of our RF cables inside of our experimental box. Well, beside of all these problems, I started tuning my cavity for several frequencies. With time, I took a first look at the resonance frequencies of a cavity. I saved these resonance frequencies. I opened my cavity, so I was using a horn antenna, exactly to say. I tuned my antenna, so the loop or the helix antenna, for the frequency I wanted to look at. When I closed the cavity again, and already now I saw a quite good matched cavity. After this pre-tuning, I was able to use my free stub tuner and reach nice peaks like this one with, let's say, S11 factors of -50 dB, for example. I don't want to say that number too loud. And also very high Q factors. Well, so I'll come to the measurements we did the last weeks and months. The first measurement was done with the original configuration, the cavity with straight or flat end caps. We used a generated power of 2 watts for the first trials. We did 200 runs with 30 seconds each in the 0 degree direction, and we used a loop antenna for power emitting. You can see 2 graphs, one with a complete thermal drift compensation. You see the red line is with power input. We have 0.8 watts of power going inside of the cavity if I trust my bidirectional coupler. And we can see a force of, well, it's noise. We have a noise of about 0.1 micronewtons. If you have a look at the just sector 1 drift compensation, we can see this behavior. We have this straight line, we have this slowly growing up force, and after turning off the power with slowly decreasing force on this device. So we can, yeah?
What is sector 1?
Sector 1 was mentioned by the presentation of Matthias. Sector 1 is the part of a measurement which is no power. Yeah?
I say a little bit more detail.
Okay.
We set up all our measurements in 5 sectors. So sector 5 is the beginning basically, so nothing happens. Sector 2 we rarely don't consider because it's we could actually increase the power in a certain time frame, but this time frame is for us 0.1 seconds, so sector 2 is irrelevant. Sector 3, yeah, we can put it in.
We will sketch.
Yeah, I think it's so
Yeah.
imagine something like
You say you
this.
flattened out part of the curve.
Yeah.
So this is 1, 2, 3, 4, 5. Okay.
Is it clear now?
2 and 4 are power on, power off?
Yes. Yes. Overall, drift compensation shows just noise, and just only respecting sector 1 we see with most likely thermal behavior. We did further measurements with same frequency, also straight end caps, but in this case with more power, even more power, up to 6 watts at my power meter at input side. Because of the 60 seconds one we now used, we had only 140 runs with 60 seconds in 180 degree direction. We also used our loop antenna, and we also saw, well, noise. The sector 1 drift compensation also shows not that very beautiful, but it also shows with thermal peak behavior, and we can also say this is not very likely thrust, but any kind of thermal drift. To compare this with the results of a NASA measurements Paul March presented at the Advanced Propulsion Workshop in 2016, they showed at 1934 megahertz and 20 watts power force of up to 90 micronewtons. We can compare this case perhaps with our 1920 megahertz 6 watt power, and we just see 0.1 micronewtons of force, which is noise. The next configuration, in according to another experiments, was 1933 megahertz with high density polyethylene dielectric inside. Our dielectric was just 4 centimeters wide, another dielectric was 5.4 centimeters wide. We generated 10 watts of power, and we saw about 3.2 or 3.3 watts of power inside of a cavity. We did 55 runs a day, that's not that fine, but results are clear, with 0 degree direction and loop antenna also. Here we can see with total thermal drift compensation a force of up to 2 micronewtons, which is not clearly above the noise, but if we just look at the sector 1 drift compensated chart, we can see that there's also no step response, and there's also this nice thermal peak at the power on level, and also the nice power force decreasing at the cool down time. So we can also assume that it is also no thrust, but just thermal behavior. To compare this again with another experiment from 2016, we have a frequency for 4 megahertz below the NASA experiment, but in this case we have the same power level. And NASA saw 4.7 micronewtons of force, and we are seeing just below 1.8 micronewtons of force. But as I already mentioned, we are seeing this nice typical thermal behavior. Next configuration, following the hint of Roger Scheuer, was a higher frequency above with 2.3 gigahertz cutoff frequency, and using spherical end caps this time, spherical for the small end cap and spherical for the large end cap. We did, I think, this case were 140 runs, which is a mistake for me. Also 60 seconds each one, 0 degree direction, and as I already mentioned, I used a helix antenna. I know helix antennas are not very useful for exciting certain modes, but well, we did their job well. The result is also complete thermal drift compensation, just noise. Sector 1 drift compensation shows not red clearly, not red beautiful, but it also shows this thermal behavior we saw already before. Well, using next geometry or another geometry, again, straight end caps with a higher frequency, for this example, 2446 megahertz at 0 degree measurement, we have again a slight force peak after thermal drift compensation and averaging, but looking at the sector 1 thermal drift compensation, we again just see with typical form of thermal drift. Well, to summarize this, to conclude this, we manufactured and characterized a copper cavity with the design, after the design of another cavity. We used straight and spherical end caps, we used different frequencies, different power levels, we used high density polyethylene dielectrics and no dielectrics, and all we see until now is just thermal effects, and I'm afraid there's no thrust observed in our experiments. Well, with our actual problems and future plans, one of the problems, as I already mentioned, is the thermal drift behavior. I assume that it could happen that the loop antenna, for example, has another thermal drift behavior than our cavity has. So, if we power our cavity, our loop antenna expands due to thermal heating, and it changes its resonance frequency, but at this moment, the cavity will not see this kind of power and will expand in another way when the antenna does. So the matching between emitting antenna and a resonant cavity or a cavity will not be the same. So we've got some problem with matching, which could be observed further. I have clearly to care about this power oscillation inside of my setting. One way to rule this out will be using another circulator inside of my inside of a vacuum chamber next to my bidirectional coupler to avoid reflecting power coming back from the cavity going to all our feed-throughs. And well, yes, next problem, really serious problem, is that our system is extremely sensitive to positioning of wires, to positioning of a cavity inside of our millimeter shielding box, ground contact, perhaps capacitive behavior. Who knows? I have to investigate it a bit deeper. Well, the last point, our future plans. Of course, we will continue testing. We will test again further frequencies. We will perhaps test other geometries. We will use thicker HDPE discs to achieve the real NASA design. I will try to handle with ground capacitive problems. And as I already said, don't trust the bidirectional coupler. I will replace this bidirectional coupler with 2 directional couplers. And perhaps the next step will be using a sensor antenna inside of my cavity to verify resonance frequencies or resonant behavior. A possibility would be to heat up our cavity to avoid thermal drift during the experiment, during the measurement. And yes, the next big step will be doing measurements on a rotary test rig. Thank you for your attention.